Hi everyone, welcome to Go Classes. In this session, we are going to study minimization of DFA. We have a deterministic finite automata. How can we minimize this so that we can get minimum number of states for the same language? We should not change the language. We should minimize the DFA for the same language. Okay, and we should get minimum number of states. Okay, so that is our topic in this session. Before we study minimization of DFA, we need to see some one or two notes we need to study. So let's see the note number one, that is unreachable state. What is an unreachable state? The name itself is telling you unreachable means we cannot reach this state from the initial state. So remember, unreachable state means a state which is unreachable from the initial state. Okay, so from the initial state we cannot reach, so that state is called unreachable state. Basically we can never reach there from the initial state. Okay, for example, look at this DFA. In this DFA, how many states are there total? In this DFA, total two states are there. Okay, so this is our DFA. In this DFA we have total two states. Let's call it, for example, this is your state Q0, this is your state Q1. Okay, so remember here the set of states is like this, 0 comma 1. These are the two states. Okay, in this DFA, in this DFA we have two states. And tell me, in this DFA, what is the final state? What is the final state in this DFA? That is your state number one. This is your final state. But you can notice that this state is unreachable. Yes or no? Can you notice that this state is unreachable? From the initial state, can you reach it? Can you reach this state from the initial state? From the initial state, can you ever reach this state number one? We can never reach it. Yes or no? So this is unreachable state. Now let me ask you, what is the language of this DFA? So this is our DFA. What is the language of this DFA? If someone asks you, that is phi. Yes or no? No string is accepted. Correct, empty language, because no string is accepted. You can see for every string the DFA will end in this state number 0, and this state number 0, this is the non-final state. So the language of this DFA, that is phi. Okay, yes or no? Now you can notice this state is unreachable. So if I remove this state, then will the language change? If I remove this state from the DFA, then will the language change? The language will not change. Yes or no? So I can say that this DFA this is equivalent to a new DFA I can create. This DFA this is equivalent to a new DFA. I can create a new DFA, okay, with single state. A new DFA I can create with a single state. So you can see this is your new DFA with a single state. Okay, the language of this DFA is also, what is the language of this DFA? That is also phi. That is also empty language. No string is accepted. Okay, so very simple. Now you can see in this DFA, this state number 2, this is unreachable. Correct? Do you agree that this state number 2, this is unreachable state? Yes or no? So I can say this is an unreachable state. This state is also unreachable. So if I remove this state, will the language change? The language will not change. Yes or no? The language will not change. You can see what the language here. Okay, let's call it DFA. So for this DFA, what the language? You can easily see the language is basically odd number of zeros. Yes or no? Okay, so here the language is a odd number of zeros. Odd number of zeros. Okay, and you can see if I remove this unreachable state, this state number 2, this is unreachable from the initial state. The initial state is this state 0. Yes or no? So this state 0 is the initial state. From the initial state we can never reach this state number 2. Yes or no? So this state number 2, this is unreachable state. Now you can see this DFA is accepting the language odd number of zeros. Now I can remove this unreachable state. The language will not change. Yes or no? So I got a new DFA. Let's call this DFA M2. Okay, and what are the language of this DFA M2? That is also the same. That is a odd number of zeros. Odd number of zeros. Okay, so very simple idea. What about this DFA? Is there any unreachable state here? In this DFA, do we have any unreachable state from the initial state? Remember, this is your initial state, correct? Okay, so this is our initial state. Okay, so from the initial state, which state is unreachable? You can see this state is reachable. Okay, on symbol 0 we can reach here. This state is reachable on 0,01. Yes or no? On string 01 we can reach here. Okay, this state is reachable on string 1 we can reach here. This is reachable on string 11 we can reach here. Okay, but this state, look at this state is unreachable. Yes or no? So I can say that this state, this is a unreachable state. Okay, and remember, we can remove the unreachable state without affecting the language. So this is a simple point. Unreachable states can be removed without changing the language. Okay, so this is a very simple point. Now let's see the next note number 2. That is, for any regular language, we have infinite number of DFA. But for any DFA, there is a unique regular language. Okay, see, very simple point. If you have a regular language, then for this language, you can create infinite number of DFAs. But if you have a DFA, then this DFA will accept a unique regular language. Okay, now let's understand this point. So let me give you a regular language. Okay, consider a regular language. What is the definition of regular language? Regular language is a language for which there exists a DFA. Yes or no? For regular languages, there exists a DFA. So let me give you a regular language that is sigma star. Okay, that is sigma star means this is AB whole star. Okay, so every string belongs to the language L. Now, for this language, I can create many different DFAs. See, notice what I can do. I can create many different DFAs. I can create a DFA with single state. Yes or no? For this language, what I can do, I can create a DFA with single state. This state number Q. Okay, and I can create this AB and I can make it final so that every string will be accepted. So you can easily see that this is your DFA for this language L. Yes or no? So this is the DFA D1 for language L. For language L, correct? Okay. So this DFA I can create. Can you create some other DFA? Can you create some other DFA? Yes, definitely I can create some other DFA. Okay, so let me create DFA D2 for language L. For example, what I can do, I can create this DFA. Look at this DFA. So on AB, I can go to a new state, and this new state is also final state. Yes or no? Now you can notice what the language accepted here. Tell me what the language accepted here. The language again is sigma star. Every string is accepted. Yes or no? So this is another DFA. Okay, can I create more DFAs? Yes, definitely. What you can do, you can create another DFA. So let me create DFA D3 for language L. Okay, for language L, I can create more DFA. For example, what I can do, I can create this DFA where this is final state, initial state itself is final state. Okay, and I can do this AB. And what I can do, see, this is your state Q0, this is your state Q0, and I can create this state Q1. Okay, now you can see this is an unreachable state, but that is fine. Yes or no? This is a valid DFA. This is a valid DFA because here you can see we have two state. This is the initial state. This is also final state. You can see every state on every input symbol has exactly one transition. Yes or no? You can notice every state on every input symbol has exactly one transition. So you can see that this is a valid DFA. And what is the language of this DFA? Tell me. What is the language of this DFA D3? That is also sigma star. Every string is accepted. So notice here we have two states where Q1, this state is unreachable. Okay, but you can see this is a valid DFA. This DFA has two states, but the language is sigma star. So for this language, we can create another DFA that is D3. So like this, we can create many more DFAs. For example, what I can do, I can create three-state DFA also. Okay, if you want, what I can do, I can create another DFA for this language. For this language, I can create DFA like this. Okay, initial state, I can make it final state. Okay, I can do this, that on B, there is a self loop. On A, I can go to a final state. Okay, here on A, there is a self loop. Okay, on B, I can go to this state, and here on A, I can make this, and on B, I can make this. Now again, you can notice every state is final state, so every string will be accepted. Yes or no? Is this clear? So what the language of D4? That is again sigma star. So can you notice that for any language we can create infinite number of DFAs for any regular language? Yes or no? So if you have a regular language L, if you have a regular language L, then remember for this regular language, we can create infinite number of DFAs. We can create, for example, DFA D1, DFA D2, DFA D3, D4, and so on. Yes or no? We can create infinite number of DFAs we can create. Like this, keep creating, no problem. Okay, what you can do, you can keep adding unreachable states. Yes or no? Add one more unreachable state, add one more unreachable state. You can create 5-state DFA. You can create 6-state DFA. You can create 100-state DFA. Yes or no? You can add unreachable states, add 97 unreachable states. Then you will get, for the same language, you will get 100-state DFA. Okay, so this is what I'm saying, that if you have a regular language L, then you can create infinite number of DFAs. Yes or no? So you can see there are infinitely many DFAs. I can create infinitely many DFAs for this language L. Okay, but the interesting question is which of them has minimum number of states? That is the interesting question. So remember what we want to ask. The interesting question here, the interesting question is which of them has the minimum number of states? Okay, so remember, okay, here remember the interesting question is here the interesting question is which of these DFAs, because we have infinitely many DFAs. Okay, yes or no? You can keep creating DFAs, keep creating DFAs. So infinitely many DFAs are there. But the interesting question is which DFA for L has minimum number of states? Okay, yes or no? Finding finding a DFA, finding the DFA. Okay, I can say finding the DFA for L which has minimum number of states. For L with the minimum number of states. With minimum number of states. Okay, so this DFA which has minimum number of states, this DFA we will call it minimum DFA, or you can call it minimal DFA. And let me tell you, this will be unique. Okay, means there will be exactly one DFA which will have minimum number of states for this language L. So for any regular language L, we can create infinite number of DFAs. You can keep creating DFA, no problem. Okay, you can keep adding unreachable states, unreachable states. You can keep adding unreachable states, and you can create infinitely many DFAs for the same regular language L. But the interesting question is finding a DFA with minimum number of states. And let me tell you, for any regular language L, this minimal DFA will be unique. Okay, means there will be exactly one DFA with minimum number of states for any regular language L. Okay, so I hope this point is clear. But you understand one more point. If I give you a DFA, if I give you a DFA, given DFA M, okay, given any DFA M, remember there will be unique regular language that this DFA will accept. Yes or no? Okay, there will be a unique regular language accepted by this DFA. Okay, so if I give you a DFA, remember, if I give you a DFA, then this DFA will accept a unique regular language. Okay, is this clear? A unique regular language will be accepted by, okay, so this given DFA accepts a unique regular language. Okay, is this clear? But if you have a but if you have a given language, but if you have a given regular language L, but if I give you a given if I give you a regular language L, then remember there can be infinitely many DFAs I can create. Okay, is this clear? I can create infinitely many DFAs, infinitely many DFAs, infinitely many DFAs for L possible. Okay, is this clear? I can create infinitely many DFAs for L. But remember, there will be a unique minimal DFA for L. There will be a unique minimal DFA for L. Okay, is this point clear? Please tell me. So this is the note. So you can see if I give you a DFA, given a DFA, this will accept a unique regular language. Okay, but if I give you a regular language, then you can create infinitely many DFAs for this regular language L. But remember, for this regular language L, there will be unique, means exactly one minimal DFA for this language L. Okay. So all these points, I hope all these points are clear. So you can see what is the definition of regular language. We have already seen a language is called regular language if it is accepted by some DFA. Some DFA means at least one DFA. Okay. So any language for which there exists at least one DFA, that language is a regular language. But I told you that if you have any regular language, then what you can do, you can create infinitely many DFAs. Yes or no? For any regular language, what you can do, you can create infinitely many DFAs for this regular language L. But the minimal DFA will be unique for any regular language L. Okay, so this is our interesting question, that basically we want to find the minimal DFA for a given regular language. Okay. Now let's study our topic, that is DFA minimization. Okay, so I told you that for any regular language we have a unique minimal DFA, means DFA with minimum number of states. Okay, so we want to find this unique minimal DFA for any regular language L. Okay, this is our task. So you can see our task, that is minimization of given DFA. Okay, here remember our task will be like this, that you have a DFA D. Okay, you have a DFA D. Now for this DFA D, what we will do? We will do the minimization. We will do the minimization of this DFA. Okay, here remember this DFA D, let's assume this is accepting language L. Let's assume this is accepting regular language L. Now you can see our task is basically we want to minimize this DFA and we want to get a new DFA. Okay, we want to get a new DFA. Let's call it DFA M. So we want to get this DFA with minimum number of states for the same language L. Okay, is this clear? Basically, we want to get a new DFA with the minimum number of states. We want to get a new DFA with minimum number of states for the same language L. For the same language L. Okay, for the same language L, we want to do this. So this is the idea. Okay, and we will call it minimal DFA. Is this clear? This type of DFA, we are going to call it minimal DFA, or we will call it MDFA. So here remember this DFA with the minimum number of states, this DFA will be called minimal DFA. We will call it minimal DFA. Okay, and in short we will write it MDFA. MDFA means minimal DFA. Is this clear? So this minimal DFA, here you can notice this minimal DFA, we will write it MDFA. Okay, in short we will write like this, that this is a minimal DFA. Okay, MDFA. MDFA means minimal DFA. Now, if you want to minimize a DFA, then there are two methods. Either you can use the first method or you can use the second method. Okay, so we will see both the method. Okay, so the first method, that is finding equivalent states and merging them. This is the method number one. Okay, and another method is that is Hopcroft partition algorithm. Okay, so there is an algorithm given by Hopcroft. Okay, that algorithm also you can apply. So remember, if you want to minimize a given DFA, a DFA is given to you and you want to minimize this DFA for the same language, you want to find a DFA with minimum number of states, then you have two methods. Either you can use the first method or you can use the second method. Now you might be thinking, sir, which method is more efficient? Which method should we apply? So let me tell you that method number one, okay, that is fast and that is more efficient, and we will apply this method in most of the questions. In majority of the questions, we will apply the method number one. And this Hopcroft partition algorithm, or I can say this Hopcroft algorithm, this we will not use in the questions. We will study this, but don't worry. Okay, so we will study this also, we will study this also, both the methods we will study. We will do a lot of practice of both the methods, but this partition algorithm, this Hopcroft algorithm, this method you should not apply on the questions. Okay, if the question is very complicated, then you can apply this method, but most of the time we will use the method number one. Okay, is this clear? So this method number one, this will be fast and efficient. Now let's start our method number one. Okay, so we want to minimize a DFA. A DFA is given to you. We want to minimize this DFA. So let's see the method number one. That is very simple. Step number one, that is remove all the unreachable states. So first you remove all the unreachable states, and then what you do, you find equivalent states and you merge them. Okay, find equivalent states. Now they are equivalent states, so we can merge those states. So these are the two steps. So the first step, that is very simple, remove all unreachable states. This is very simple step. Okay, now you might be thinking, sir, how to find equivalent states? What are equivalent states? Okay, then we can merge those states. So now our next topic, that is equivalent states in a DFA. Equivalent states, we can also call it indistinguishable, means these are not distinguishable. So remember, equivalent, another word is indistinguishable, another word is mergeable states, or I can say identical states. So these are the different names for the same topic. I can say equivalent, you can call it equivalent states, or you can call it indistinguishable states, or you can call it mergeable states, or you can call them identical states. Now what are equivalent states? So let's see. So let's see this equivalent states. So when can I say that two states are equivalent? Okay, so this is our topic. So let's see, if you have two states, states P comma Q are equivalent. When can I say that these two states are equivalent? Equivalent means indistinguishable, remember. Okay, so when can I say that two states are equivalent? So let's see the definition. Understand the definition very carefully, because definition is very important. Okay, so we have two states. When can I say they are equivalent? Equivalent simply means that these two states will go to final state together and they will go to non-final state together. Okay, this is a simple point. Basically, what I can say, two states are equivalent. When can I say two states are equivalent? When for every string, When for every string W, remember for every string W, what should happen? For every string W, either this should happen or this should happen. Okay, what should happen for every string W? Remember, for any string W, I can say whatever string you take, for any string W, whatever string you take, either this should happen or this should happen. What should happen? See, so if P is going to final, then Q should go to final. If P is going to non-final, then Q should go to non-final. Very simple point. Okay, this is your state P, this is your state Q. Remember, on any string W, on any string W, okay, either both are going to final, either both are going to final state, okay, or both are going to non-final state. Either both are going to final state or both are going to non-final state. Is this clear? Tell me. So you have two states P comma Q. When can I say these two states are equivalent? They are equivalent if for every string, means for any string, remember, either both will go to final or both will go to non-final. It will not happen that one of them is going to final on W and another is going to non-final on W. It will not happen. Okay, is this clear? So equivalent state simply means that they will go to final together, they will go to non-final together. For every string, this will happen. For any string W, this will happen, that both will go to final or both will go to non-final. Okay, is this point clear? Let me know. So this is a simple point, that this is the definition of equivalent. So remember, when can I say two states are equivalent? I can say two states are equivalent if for every W, for every string W, what should happen? For every string W, this should happen that if P is going to final, okay, I can say means delta star PW. If P is going to final, means if P is going to final states, okay, if P is going to final state, remember F, then remember Q should go to final state. Then remember Q should go to final state. And if P is going to non-final, then Q should go to non-final. So very simple. So remember, this is if and only if. Okay, is this clear? So very simple point. When can I say two states are equivalent? If for every string this should happen, that if this P is going to final, then Q will go to final. If P is going to non-final, then Q will go to non-final. So this is the simple idea, that for any string, whatever string you take, either both will go to final or both will go to non-final. This is the definition of equivalent states. Now let me tell you what the definition of non-equivalent states means. What the definition of distinguishable states? Distinguishable. When can I say two states are distinguishable? Distinguishable means not equivalent. Yes or no? Distinguishable simply means not equivalent. Okay, this simply means not equivalent. So when can I say two states are not equivalent? So let's see this. So you have two states P comma Q again. Now when can I say they are not equivalent? When can I say they are distinguishable? When for some string, for at least one string, remember, for at least one string W, for some string W, remember, for at least one string W, what should happen? For at least one string W, this should happen, that P is going to final and Q is going to non-final, or P is going to final, Q is going to non-final. Okay, so remember, what should happen? Two states are distinguishable. When can I say they are distinguishable? If for some string, for at least one string, what should happen? This should happen that P is going to final on W, P is going to final, Q is going to non-final on W. Okay, or P is going to non-final, P is going to non-final, and Q is going to final. Okay, is this point clear? So this is the idea, that for some string, P is going to final, Q is going to non-final, or P is going to non-final, Q is going to final. So this type of situation, then I can say that this state P comma Q, they are distinguishable, or I can say not equivalent. Is this point clear? Please tell me. Okay, so very simple. Now we will do a lot of practice, and then this concept will become very clear. But remember this point, when can I say two states are equivalent? When can I say two states are equivalent? Equivalent P comma Q. Two states P, Q, two states. When can I say they are equivalent? Remember, equivalent simply means whatever string you take, either they will go to final or they will go to non-final. Both will go to final or both will go to non-final, whatever string you take. Okay, yes or no? Is this clear? Whatever W you take, either both will go to final or both will go to non-final. This is the idea. Okay, and what are the definition of distinguishable? Two strings, sorry, two states are distinguishable. Two states are not equivalent if for some string one of them is going to final, another is going to non-final. Okay, we will do a lot of practice. All these concepts will become very clear. So let's start with this example. A DFA is given to you. So here you can see this is your, let's call it DFA D. Okay, now in this DFA D, tell me, state B comma A, are they distinguishable or not distinguishable? Tell me. Let's check. Let's check state. Let me check state A comma B. Okay. What about these two states? Can I say they are equivalent or they are not equivalent? Tell me. See, you can easily see that this is your state A. Okay. And this is your state B. Now you can easily see that. Look at this string 0. For string 0, what is happening? See, for string 0, you can easily see that state A is going to non-final. State A is going to non-final. Okay, state A on this string 0, state A is going to non-final and state B is going to final. Yes or no? Is this clear? See, very simple point. I am checking this state and this state. Now you can easily see that on string 0, you can see this A is going to non-final. Okay, A is going to non-final, but B is going to final. So you can see there exists a string. Yes or no? Because of this string, one of them is going to final, another is going to non-final. So what I can say? I can say these states are distinguishable. Is this clear? So I can say that state A comma B, they are not equivalent. Remember, state A comma B are not equivalent, or I can say distinguishable. Is this point clear? That they are distinguishable means they are not equivalent. I can say that A comma B, these two states are not equivalent, and I can say they are distinguishable by string 0. Yes or no? Because at least one string is enough to distinguish them. Okay, what are the definition of distinguishable states? Two states are distinguishable if for some string one of them is going to final, another is going to non-final. Yes or no? So here you can notice that these two states A comma B, these two states, they are distinguishable by 0. Okay, so I can say that these two states, remember, I can say state A comma B are distinguishable by string 0. There can be more strings, don't worry. Okay, at least one string is enough. So you can see these states are distinguishable by string 0. String 0. Okay, very simple point. Now, what about state B comma C? Can anyone tell me? What about state B comma C? Can you tell me? Are they distinguishable or not? What about state B comma C? See, you can easily notice. What about empty string? You can see that on empty string, this will go to non-final, this will go to final. Yes or no? So you can see that they are not equivalent. Okay, because what will happen? This is your state B, this is your state C. Look at what will happen on empty string. On empty string, you can see this state B is going to non-final and this state C is going to final. Yes or no? On empty string, this B is going to B, which is non-final. C is going to C, which is final. So you can see that on this string, these states, one of them is going to final, another is going to non-final. So I can say that these two states are also not equivalent. Is this clear? So you can see that these two states, they are also not equivalent. I can say they are also distinguishable, and I can say they are distinguishable by empty string. Yes or no? Okay, so I can say that state B comma C are distinguishable by empty string. Is this clear? They are distinguishable by empty string. Is this point clear? Please tell me. So they are also not equivalent. Now, can you notice one point that what about state D comma G? What about state D comma G? Tell me. Similarly, what about state D comma G? See, state D is also not equivalent to G. Why? What is the reason? They are distinguishable by empty string. Yes or no? They are also distinguishable by empty string because you can see this state on empty string, this is going to non-final, this is going to final. So you can see that state D comma G, they are also distinguishable by empty string. Can you notice a final state and a non-final state, can can they ever be equivalent? Tell me. You have a final state, okay, you have a final state, okay, and you have a non-final state. Can they ever be equivalent? Is it possible they can be equivalent? They can never be equivalent, right? Because what will happen on the empty string? See, notice what will happen on the empty string. On the empty string, Q1 will go to final and Q2 will go to non-final. So what I can say, I can say that these two states are never equivalent. A final and non-final state, they can never be equivalent. Yes or no? Is this point clear? A final state, a non-final state, they can never be equivalent because they are distinguishable by empty string. Okay, they are distinguishable by empty string. So this is very simple point. So you can easily see a final state and a non-final state are never equivalent. Okay, remember they are never equivalent because they are distinguishable by empty string. Now let's move on. So remember, you don't have to check a final and non-final state. Yes or no? You don't have to check CE. You don't have to check DG. You don't have to check BG. Yes or no? These things you don't have to check. Okay, is this point clear? So you have to check only the non-final states and you have to only check the final states. So remember, these two states you will compare. Also, you will compare these states. So this is the point. Okay, is this point clear? So now you tell me, what about state C comma G? Let me know. What about state C comma G? Both are final. Both states are final. Are they equivalent? Can you tell me, are they equivalent? Yes, they are equivalent. Notice, on every string, this will go to final. On every string, this will also go to final. See, notice one thing. Whatever string you take, okay, whatever string you take, any W you can take, any string W you can take, what will happen? This C is also going to final, G is also going to final. Remember, we only care about final or non-final. We only care about going to final or non-final. We don't care that this is going to C, this is going to G. They are going to different states. Please understand that we don't care about the different state. For example, C comma G, they are different states. We don't care. We only care, are they final, are they non-final? Are we going to final, are we going to non-final? For us, only this matters. Are we going to final? Are we going to non-final? So remember, this state C comma G, they are equivalent. Why they are equivalent? Because whatever string W you take, any W you take, this will also go to final. This will also go to final. Yes or no? So I can say that for every string, this is happening that both are going to final. So they are equivalent. Is this clear? Please tell me. So these states are equivalent. Okay. Is this clear? So we can merge them, remember, because these states are equivalent. So we can actually merge them. Okay, we can merge and we can make single state. So remember, okay, here let me write it. Since state C comma G are equivalent, since these two states are equivalent, we can merge state C comma G. Okay, and we can make a single state. So remember, we can merge state C comma G and we can make a single state. It will be like this. What we can do, we can remove this. Okay, we can remove this and we can basically make a single state. We can basically make a single state and it will happen like this, that okay, a single state we can make. So a single CG, I can call it CG. Basically, we are merging these two states. So a single state I can make. Okay, and it will be like this. On 0, you will go here. Okay, from here also on 0, you will go here. And it will be 0, 1. So this is the idea. I hope this point is clear. Okay, let me know. Now, what about the state B, comma E? What about these two states? Please tell me. What about state B, comma E? Let me know. These two states, they are non-final state. Are they equivalent or are they not equivalent? You can easily see they are not equivalent. What about string 0? They are distinguishable by string 0. So remember, this is your state B, this is your state E. You can easily see this string 0, on this string 0, this state B is going to final, this state E is going to non-final. Okay, so that is very simple point and I can easily see that. So I can say that they are not equivalent. Okay, is this clear? They are not equivalent. What about E comma D? What about state E comma D? Tell me. What about state E comma D? Let me know. So again, you can easily see this E state and D state. Are they distinguishable or not? Let me know. You can easily see, for example, 0, 0, 0 on this string. On this string, remember, on this string, what will happen? On this string W, what will happen? This state D will go to final and this state E will go to non-final. Yes or no? So that is the reason I can say that they are also not equivalent. E is not equivalent to D. Is this point clear? Please tell me. So they are also not equivalent. Okay. Tell me, this state E, is this unreachable? Is the state E unreachable? No, this is reachable. This is reachable. 0 1, yes or no? On the from the initial state on string 0 1, this state E, that is reachable. What about state D? Yes, state D is unreachable. Yes, very good. So state D is unreachable, we can remove it. Okay, we don't even have to check it. This is unreachable. Okay, so because this is unreachable, you should remove it in the beginning. Okay, because it is unreachable. So remember, in the beginning, you should remove it. You should remove it because it is unreachable. So you should remove it. Very simple. Is this point clear? Because this is unreachable, so we should remove it. Okay, very simple. Now, now you tell me. So we have seen that these two states, they are equivalent. Now tell me, what about B comma F? You tell me about B comma F. What about state B comma F? Are they equivalent or not? Let me know. State BF. Okay. See, notice one thing. This is your state B, this is your state F. Okay. On the empty string, where are they going? Tell me. On the empty string, where are they going? This state B is going to non-final. This state F is also going to non-final. Okay. So here they are going, both are going to non-final. Yes or no? On symbol 0, where are they going? On symbol 0. On symbol 0, where are they going? So you can see on symbol 0, this B is going to final and this B is going to final, and you can easily see F is going to final. Okay, on symbol 0. You tell me one thing. You tell me one thing. See, already we have seen that these two states, they are equivalent. Yes or no? CG, they are equivalent or not? Already they are mergeable. Yes or no? Already they are. You can say that they are your state mergeable. These are already, basically we are already merging them. Yes or no? These states are already mergeable. So what about 0W? Like after 0, if something comes, what about these strings 0W? See, a very simple point. What I'm saying that state BF, this is your state B, this is your state F. Okay. On 0, what is happening? On state 0, on string 0. See, on string 0, both are going where? Both are going to the same state, that is CG. Because that is, this is a one state, this is a single state, I can say CG, that is a single state. Do you agree? Okay, so you can see this state BF, this state B and this state F. On 0, they are going to same state. So now whatever comes, okay, now whatever comes, what will happen? They will always go to final or non-final together. Do you agree with me? Yes or no? They will always go to final together. They will always go to non-final together. I can say that they will always remain together. Is this clear? Okay, so very simple. I can say that this state BF, you can see on these strings, on this type of strings, they will always be together. On this type of strings, on this type of strings, I can easily say that they will always be together. Okay, yes or no? They will always be together. Either, okay, yes or no? They will always be together. Now, so what about string 1? What about string 1? Tell me. On string 1, both are going to non-final. Both are going to non-final. Now, again, you notice what will happen. See, this state B and this state F on string 1, on string 1, they are going to state E. Both are going to state E. Yes or no? They are going to state E. Now you can notice, now whatever comes, they will be together. Now whatever comes, they will be together. So remember 1W, whatever comes, what will happen? I can say they will be together. Do you agree? So this state BF on string 1, they are going to E. Now they are meeting here. They are meeting here. Now whatever W comes, they will remain together. Okay, so that is the reason. Can I say that BF, they are equivalent? B is equivalent to F, because you can see that whatever string you take, remember, whatever string you take empty string, or you take starting from 0, you take starting from 1, whatever string you take, they are always going to final, non-final together. Yes or no? You can notice they are always going to final, non-final together. They are always going to final, non-final together. Yes or no? So that is the reason I can say that they are equivalent. Did we check every string? Please tell me. Did we check every string? Yes, we are checking every string. You can see we are checking empty string. We are checking starting with 0. We are checking starting with 1. So every string we are checking. So you can easily see that they are equivalent. Okay, is this point clear? So remember, these two also I can merge. Remember, D is unreachable. So this state D you can remove. Okay. And these two states, this CG, this CG is a single state. Okay, so I can say that, what I can say, I can say this CG is a single state. This has become your CG. Yes or no? This state, this is your CG state. Okay, and one more thing, BF, these two states, they are also mergeable. Yes or no? We can merge them. We can merge them. Okay, so finally, if you merge them, then tell me what you are getting. Let me know what you are getting. So you are getting this type of, remember, on 0 1 you are going to BF. Okay, and from here on 1 you are going to state E, and remember from here, so on one you are going to state E, and from here on 0 you are going to state CG. Now tell me, so this is what you got. Now you tell me one thing. Now in this state, any two states are equivalent or not? For example, what about these two states? E comma B, A comma BF. What about these two states? Let me know. Okay, so remember we got this. Remember we got this state number A. Okay, on 0 1 we are going to this state BF. From state BF, remember on symbol 1 we are going to state E, and on symbol 0 we are going to state CG, which is final. Okay, now you tell me, is this minimal or not? Now can we merge something? Is it possible we can merge something? Is it possible? No, now this is minimal. Now this is a minimal DFA. Why this is a minimal DFA? Because we cannot merge anything. Okay, for example, what about ABF? What about ABF? Tell me, what about these two? Are they mergeable or not? No, they are not mergeable. For example, you can easily see, what about, you can see, which string will distinguish them? Tell me a string which will distinguish them. That is 0. Okay, this state A will go to non-final, and this state BF will go to final. So you can easily see that A is distinguishable from BF. Okay, and they are distinguishable by 0. Yes or no? Is this clear? They are distinguishable by string 0. So very simple point. And you can see, what about AE? Let me know, what about AE? Tell me, what can you say about AE? Check for AE. So let's check for AE. A comma state E. So you can easily see which string will distinguish them. Which string is going to distinguish them? That is, for example, 0 0. Yes or no? A will go to final and E will go to non-final. Yes or no? So very simple. They are also distinguishable. What about BF comma E? What about BF comma E? So you can see they are distinguishable by 0. This state BF will go to final and this state E will go to non-final on 0. Okay, so that's it. So that is the reason I can say now this is a minimal DFA. Okay, is this clear? This DFA is minimal because all these states, they are distinguishable. No two states are equivalent now. Now no two states are mergeable. All states are distinguishable. So this is the minimal DFA. I hope this point is clear. So remember, this DFA we can minimize and we will get minimal DFA will have how many states? Minimal DFA will have how many states? For this DFA, minimal DFA will have only 4 states. There will be 4 states in the minimal DFA. And remember, this is unreachable state. So in the beginning, you can remove it. Because this is unreachable state. So in the beginning, we can remove it. Very simple point. And the minimal DFA will have 4 states. Now let's move on. So I told you one thing. When we are checking for equivalent states, we only care about final comma non-final. Yes or no? We only care, are we going to final, are we going to non-final? We don't care in which state we are going. For example, let's assume that you are going to state Q, I am going to state P. But we only care, are these final or are these non-final? Okay, is this clear? We only care about final comma non-final. We don't care about, are we going to different states or are we going to same states? We don't care. We only care, are we both going to final or are we both going to non-final? Okay, is this point clear? Now let's see this example. In this example, let's call it state number 1, state number 2, state number 3, state number 4. Okay, so these are the states. Now here you can see state 2, 3, they are final states. Now in this example, you quickly tell me, Which states you will check? Will you check state 2 comma 4? Will you check state 2 comma 4? No, you will not check, because final and non-final state can never be equivalent. Yes or no? For example, 2 comma 4, they are not equivalent. Why? Tell me, what is the reason? Because this 2 is final and 4 is non-final, so they are distinguishable by empty string. They are distinguishable by empty string. So you never have to check a final and non-final state. You never have to check. You have to check 1 4 and you have to check 2 3. Yes or no? So remember, you have to check 1 4 and you have to check 2 3. So only these two things you have to check. You have to check this, you have to check this. Now first you check this 2 3 and tell me, are they equivalent? Let me know. You check for state 2 3. Are they equivalent? State 2 comma 3. See, on every string you can easily see this is your state 2, this is your state 3. On empty string they will go to final. Yes or no? On empty string they will both go to final. On empty string, both are going to final. But you can see on every other string, any non-empty string, any string other than epsilon, see, on any other string what will happen? Both will go to non-final. Do you agree? Both will go to non-final. So I can say they are equivalent. Is this clear? So I can say state 2 and 3, they are equivalent. They are equivalent. State 2 3 are equivalent. Is this point clear? Please tell me. So because they are equivalent, we can merge them. Okay, we can merge them. So remember, we can merge them. What about 1 comma 4? What about 1 comma 4? Tell me, state 1 comma 4. They are not equivalent. Okay, why they are not equivalent? State 1 4. Which string will distinguish them? Give me a string which will distinguish them. You can give string A. On string A, 1 will go to final. Okay, and this 4 will go to non-final. So you can easily see that state 1 is not equivalent to 4. Okay, is this point clear? So finally, what is the minimal DFA? What will be the minimal DFA? Remember, there will be 3 states. Yes or no? State number 1, there will be 3 states. Okay, on AB, we are going to state 2 3, which is final. And on AB, we are going to state 4. So there will be 3 states in the minimal DFA. This is your minimal DFA. Very simple. Do you agree? Okay, please tell me, did you understand? So very simple. Remember, when you minimize this, these states are equivalent. So you can merge these 2 states. Finally, the minimal DFA will have 3 states. Okay, yes or no? Like this will be your minimal DFA, 3 states. Now let's see this example. In this DFA, tell me which states you will check. Will you check 1 comma 2? Will you check state 1 2? No, you will not check, because this is final, this is non-final. They are definitely not equivalent. State 1 2 are not equivalent. State 1 0 are not equivalent. So what you will check? You will only check the state 0 comma 2. Yes or no? Is this clear? So what you will do here, remember, you will only check state 0 comma 2. These 2 states you will check 0 2. These 2 states you will check. Okay, now you tell me, what about these 2 states? Notice one thing. On empty string, they are both going to non-final. Both are going to non-final. 0 comma 2. On empty string, they are going to non-final. Okay, you tell me about 0. On 0, where are they going? On 0, both are going to final. Okay, now what about 0 followed by W? What about strings which are starting with 0? What about these strings? Notice this state 0 and this state 2. Okay, these 2 states. Notice what is happening. On 0, this state 2, state 0. On 0, they are going to 1. Okay, yes or no? On symbol 0, they are going to state 1. They are going to state 1. Okay, now from here, they will always remain together. Do you agree? They will always remain together. Yes or no? Is this point clear? See, very simple. State 0 comma 2. On 0, they are going to state 1. Okay, see, this is state 0. On 0, on symbol 0, this is going to state 1. And this is also going to state 1 on symbol 0. So both the state on symbol 0, they are going to state 1. And from here, whatever comes, they will always remain together. So this is what I'm saying, that on these strings, which are starting with 0, they are always together. They are always going to final together, going to non-final together. Basically, they will always be together. What about string 1? What about this string 1? Tell me. On string 1, both are going to non-final. Both are going to non-final. What about string 1 followed by anything? What about these strings? 1 followed by anything. Please tell me. Very simple point. Again, you can easily see that this state 0 and this state 2. On 1, where are they going? On string 1. On string 1. Both are going to state 0. Yes or no? Can you notice? See, this is also going to state 0. And on 1, this is also going to state 0. Both are going to state 0. Now, from here, whatever comes, they will be together. Whatever comes, they will be together. Do you agree? Yes or no? So this is what I'm saying, that okay, on these strings which are starting with 1, on these strings which are starting with 1, you can notice that they will always be together. Did we check all the strings? Did we check all the strings? Yes, we have checked empty string. We have checked strings starting with 0. We have checked strings starting with 1. Yes or no? Strings starting with 0, strings starting with 1, and empty string. All the strings we have checked. So finally, I can say that state 0, 2, they are equivalent because they are going to non-final together. They are going to final together. Yes or no? So I can easily say that state 0 is equivalent to state state 2. Okay, so we can merge them. Is this clear? So this and this state we can merge. We can easily merge. So finally, remember, so these two states we can merge because they are equivalent. So finally, what is the minimal DFA you will get? The minimal DFA will have only two states. Remember, the initial state will become your 0, 2. Okay, and the final state will be your 1. So there is a self loop on 1, and here you can notice there will be self loop on 1, and on 0 you will go here, and on 0 you will go here. So this is the minimal DFA. Tell me, what is the language of this DFA? What is the language here? The final state is this state 1. So the language is odd number of ones, odd number of zeros, odd number of zeros. This is the language. Okay, is this clear? Please tell me. So you can see this DFA is not minimal. We can merge state 0, 2, and finally we will get this DFA. And this is a minimal DFA. This is a DFA with minimum number of states. So we have seen the concept of distinguishable states and indistinguishable states. Yes or no? When can we say two states are equivalent? When can we say two states are not equivalent? So remember, two states of a DFA, state P, Q of a DFA are indistinguishable, means equivalent. When can I say they are equivalent? They are equivalent if on every string both will go to final or both will go to non-final. Yes or no? On every string W, remember, if P is going to final, then Q will go to final. If P is going to non-final, then Q will go to non-final. Means they will go to final together, they will go to non-final together. Okay. And when can we say that state P, Q are distinguishable? They are distinguishable, means not equivalent, if there exists a string, for some string, remember, for some string W, one of them is going to final, another is going to non-final. Okay, one of them is going to final, another is going to non-final. Then we can say state P, Q, they are distinguishable, or I can say not equivalent. And remember, this is a very simple point. If P, Q are equivalent, and let's assume Q, R are equivalent, then can I say that all three will be equivalent? Tell me. See, P is equivalent to Q. Q is equivalent to R. Can I say they also will be equivalent? Yes, here all the three will be equivalent. Yes or no? Is this clear? Notice, if P is equivalent to Q, Q is equivalent to R, then easily we can say that P will be equivalent to R, and I can say that all three will be equivalent. Yes or no? All three states will be equivalent in this type of situation. Okay, now let's move on. So how to minimize the DFA? If a DFA is given to you, then for the minimization, first step is you remove the unreachable states, and the second step is you merge the equivalent states. Yes or no? You find what states are equivalent and you merge them. So these are the two steps to find minimization of DFA. Okay, first you remove the unreachable states. Remember, first we have to remove the unreachable states. Then we have to merge the equivalent states. Okay. Let's see this example. Is this DFA minimal? Quickly tell me. This is a very nice question. Is this DFA minimal? So let's check it out. Here, which states you will check? Tell me. You can see these are the final states and these are the non-final states. Which states you will check? You will check the non-final states and you will check the final states. Yes or no? Okay, so now you tell me. Now you tell me. What about state Q1, Q2? What about state Q1, Q2? Are they equivalent or are they not equivalent? Tell me. These states, are they equivalent or are they not equivalent? They are not equivalent, because you can see that which string will distinguish them? Which string will distinguish them? Tell me. So you can easily see string 0. On string 0, this state Q1 is going to final and state Q2 is going to non-final. So I can say they are not equivalent. Yes or no? Is this clear? So I can say that state Q1 is not equivalent to Q2. Okay. So definitely we cannot merge them. Okay, we cannot merge. So remember, Q1, Q2 cannot be merged. Q1, Q2 cannot be merged. Okay. What about Q0, Q3? Tell me, what about Q0, Q3? State Q0, Q3, both are non-final. So what about these states? Q0, Q3. Tell me, these states. Here you can easily see which string will distinguish them. Tell me, which string? Is there any string which will distinguish them? Do we have any string which will distinguish them? A student is saying 0, 1. See, this Q3 on 0, 1 going to final and Q0 on 0, 1 going to final. Okay. So now you tell me, you can see what will happen on 1, 0. Okay. What will happen on 1, 0? Tell me what will happen on 1, 0. This Q0 on 1, 0 going to final and Q3 on 1, 0 going to non-final. Okay. Is this clear? So remember, they are not equivalent. Is this clear? So Q0, Q3, they are not equivalent. Q0, Q3, they are not equivalent. Okay, is this point clear? They are not equivalent. They are distinguishable by 1, 0. They are distinguishable by 1, 0. Okay, string 1, 0. By string 1, 0, they are distinguishable. Is this point clear? Please tell me. So this is minimal DFA or not? The answer is yes. This is already minimal DFA, because remember, they are distinguishable. They are distinguishable. We cannot merge these two. We cannot merge these two. So this is a minimal DFA. Please tell me, is this point clear? Let me know. Okay, did you understand? So you can see this string 1, 0. Look at this string 1, 0. This Q0, Q3, they are distinguishable by string 1, 0. On string 1, 0, Q3 is going to non-final and this Q0 is going to final. Okay, so finally I can say yes, this is a minimal DFA. Okay, so the question was asking, is this minimal DFA? The answer is yes. Now let's see the next one. What about this one? In this DFA, which states are distinguishable, which states are not distinguishable? Tell me. See, a very simple point here. Look at these states. Okay, look at these states. 3, 4, 5. Look at these 3, 4, 5 states. Tell me, can you notice these states are equivalent because they are always going to final state? Yes or no? 3 is equivalent to 4, 4 is equivalent to 5. They are equivalent. Do you agree? These three are equivalent because they will always go to final. Whatever string you take, remember, whatever string you take, this will go to final, this will go to final, this will go to final. Do you agree? Do you agree? 3, 4, 5. State 3, 4, 5. Whatever string you take, on every string, they will go to final, final, final. Okay, yes or no? So I can say they are equivalent. 3, 4, 5 are equivalent. So remember, these we can merge. We can merge them. We will get a single state. Instead of these, we will get a single state. Now you tell me, what about state 0, 1? What about state 0, 1? You tell me. State 0, 1. State 0, state 1. So you can see they are distinguishable by whom? By A. This 0 on A will go to non-final state. 1 on A will go to final state. Yes or no? So they are not equivalent. So 0 state is not equivalent to 1 state. What about 0, 2? Similarly, 0, 2 are also not equivalent. State 0, 2, they are also not equivalent. You can see that on symbol B, this state 0 will go to non-final and state 2 will go to final. So again, I can say that these two, 0 is not equivalent to, state 0 is not equivalent to 2. Okay. So what is remaining? Now we have to check 1, 2. Yes or no? Now we have to check 1, 2. Remember 3, 4, 5, they are single state. Please understand that 3, 4, 5 is a single state. We have already seen this is a single state. This is a single state. Yes or no? Because we can merge 3, 4, 5, we can merge. So this is a single state. Now you tell me about 1, 2. What about state 1, 2? What can you tell me about state 1, 2? So state 1, 2, remember, on empty string, both are going to non-final. Okay. On every other string, what will happen? On every other string, what will happen? Tell me. On every other string, they will be together. Yes or no? On every string other than empty string, what will happen? They will always go to final. So can I say they are equivalent? Yes or no? Notice one thing very simple, that on empty string both are going to non-final. So on empty string both are together. And you can see on any string W, other than empty string, on any string W, they are both going to final. So very easily I can say that they are equivalent. So state 1 is equivalent to state 2. Okay. So finally, what is the answer? Tell me. So remember, these two I can merge. The answer will be like this. These two I can merge, and these three I can merge. In the minimal DFA, how many states? Tell me, the minimal DFA will have how many states? The minimal DFA will have 3 states. There will be 3 states in the minimal DFA. Okay, you can easily create the minimal DFA. That will be like this. This is your state 0. Okay, state 0. On symbol A, B, it will go to state 1, 2. Okay, on symbol A, B, this will go to state 3, 4, 5. 3, 4, 5. Okay, is this clear? So this is your minimal DFA. Minimal DFA will have 3 states. Very simple. Tell me about this one. In this DFA, you tell me which states are equivalent, which states are not equivalent. First of all, you tell me, will you check state 1, 3? Are you going to check state 1, 3? No. This is final, this is non-final. They are never equivalent. A final state is never equivalent to a non-final state. So you have to check 0, 3, 4. See, what you have to check, please notice, we have to check 0, 3, 4. We have to check 0, 3, 4. Also, what we have to check? We have to check 1, 2, 5. Yes or no? This is what we need to check. Okay, now you tell me about 1, 5. Tell me quickly state 1, 5. State 1, 5. Let me know. Are they distinguishable or not? Yes, they are distinguishable. Okay, they are not equivalent. 1, 5 on symbol A. On string A, 1 is going to non-final and 5 is going to final. Okay, so definitely they are not equivalent. Yes or no? So state 1 is not equivalent to 5. Similarly, state 2 is not equivalent to 5. Yes or no? Similarly, state 2 is not equivalent to 5. Okay. What about state 1, 2? Or you tell me about state 3, 4. First, you tell me state 3, 4. Let me know. What about state 3, 4? They are non-final. Are they equivalent? See, on every string, they are going to, you can see they are going to state 5. See, what is happening? This is state 3, this is state 4. On empty string, both going to non-final. Okay, on every other string other than empty string, on every other string, what will happen? On every other string, what will happen? Both will go to final. Do you agree? Do you agree that this state 3, 4, on empty string, they are going to non-final. This 3 is going to non-final, 4 is going to non-final. On every other string, what is happening? They are going to final. So I can say state 3 is equivalent to 4. Yes or no? State 3 is equivalent to 4. So I can merge them. Yes or no? So very simple point that these two I can merge. You can consider them as same state. What you can do, you can consider them as the same state. Remember they are same state. This 3 4 they are single state. You can consider them as single state 3 4. Okay, let me know, is this point clear? Now you tell me, okay, this 3 4 this is a single state 3 4. Now you check 1 2. Now what about state 1 2? State 1 2, yes, they are also equivalent. Now you can easily see state 1 2 are equivalent. Why? State 1 2, why they are equivalent? You can see on empty string both are going to final. Okay, now on string a comma b, what will happen? See what will happen. Strings which are starting with a, what will happen? And strings which are starting with b, what will happen? Tell me. See, very simple. This is your state. I am asking state 1, state 2. Okay, now you notice these two states on string starting with a. If string is starting with a, both are going where? 1 comma 2. On a, where are they going on a? They are going to 3 4. That is a single state. Yes or no? Now after that, whatever comes, they will be together. After that, whatever comes, they will be together. Final or non-final, they will always be together. Together in final, together in non-final. Yes or no? Similarly, this state 1 comma 2. On b, where are they going? On b, they are going to 3 4. Yes or no? On b also, they are going to the single state. Remember, this 3 4 is a single state. This is a single state 3 4. So remember, both are going to 3 4. That is single state. Now whatever w comes, they will be together. Now whatever w comes, they will be together. So this is what I'm saying. If string is starting with aw, then also they are together. And if string is starting with b, then also they are together. So string is starting with a or string is starting with b, they are always together. So I can say that state 1 and 2 they are equivalent. State 1 comma 2 are equivalent. Is this point clear? Let me know. So I can merge them. These two also I can merge. So remember, final point. Finally, I'm saying that these two I can merge, these two I can merge. So in the minimal DFA, how many states? So minimal DFA will have total 4 states. Okay, is this clear? You can see no other states are mergeable. No other states are equivalent. Okay, you can see this state 1 is not equivalent to 5, state 2 is not equivalent to 5, state 3 is not equivalent to 0, state 0 is not equivalent to 4. So no other states are mergeable. So remember, minimal DFA will have how many states? Minimal DFA has 4 states. There will be 4 states. Very simple. You can see this will be your minimal DFA. You can easily check. A student is asking, can we merge 0 after merging 3 4? See, after merging 3 4, tell me 0 and 3 4 are they equivalent? You tell me about 0 comma 3 4. Are they equivalent? 0 comma 3 4 are they equivalent? They are not equivalent. On symbol A, 0 and 3 4 are they equivalent? They are not equivalent. Tell me what is the reason? Tell me some string which will distinguish them. Give me a string which will distinguish them. Yes, AB. On string AB, what will happen? Notice on string AB, what will happen? This 0 on AB will go to non-final, and 3 4 on AB will go to final. Is this clear? Please tell me. So check two length string. Basically, AB. Using AB, you can check that the 0 is not equivalent to 3 4. Is this point clear? Please tell me. Did you understand this? Okay, so you can check two length strings. Remember one thing. When can I say two states are equivalent? When can I say two states are equivalent? Equivalent simply means that on every string, they will go to final, non-final together. Whatever string W you take, remember, we have to check all the strings W. Whatever string W you take, they will go to final together, they will go to non-final together. Okay. And when can I say they are not equivalent? When can I say they are not equivalent? If some string w, if some string w, if there is a some string w, if there is at least one string w, there is at least one string w, such that one of them is going to non-final, another is going to final, then they will be not equivalent. I hope this point is clear. Now let's move on. Minimize the following DFA. A DFA is given to you. Let's minimize this. You tell me which states you will check. First, you tell me which states are there to check. You can see this is the only final state, so there is nothing to check with Q5. Do you agree? There is nothing to check with Q5. Okay, is there any unreachable state? First, you remove unreachable state. Is there any unreachable state? Yes, Q2 is unreachable. Yes or no? I can say Q2 is unreachable. So first you remove it. This is your first step. Step number one. First you remove unreachable state. So this state is gone. Okay. After this state is gone, now you tell me. Now you tell me which states you will check. This is the only final state. So there is nothing to check with Q5. You are going to check Q0, Q1, Q3, Q4. Yes or no? So tell me, what about Q0, Q1? Let me know. Let me know Q0, Q1. What about these? Are they equivalent? Q0, Q1? Tell me. No, they are not equivalent. See, on string 0, 1, what will happen? On string 0, 1, this Q0 is going to non-final and Q1 is going to final. So they are not equivalent. Yes or no? On 0, 1. Agree? So you can easily say that they are not equivalent. Q0, Q1, they are not equivalent. Very easy. Now you tell me about the next. For example, you tell me which states are equivalent. Okay, first you remove, remember? First you remove this Q2 is gone. Okay, this Q2 is already gone. Now you tell me. Q2 was unreachable, so you can remove Q2. Okay, now you tell me here. See, Q3, Q4. Okay, are they equivalent? Please tell me about Q3, Q4. Are they equivalent or not? You check state Q3, Q4. Check it. This is state Q3, this is state Q4. Are they equivalent? So you can easily see on empty string, both are going to non-final. Okay. If string is starting with 0, then where are they going? And if string is starting with 1, where are they going? See, very simple point. This Q3, Q4. You have Q3, you have Q4. Where are they going if string is starting with 0? You can easily see on 0, both are going to the same state. On 0, both are going to Q4. Yes or no? You can see on 0, this is going to Q4. On 0, this is going to Q4. So on 0, both are going to Q4. Now here, whatever comes, they will always remain together. Do you agree? Now whatever comes, they will always remain together because Q3, Q4, they are meeting in Q4 on string 0. On string 0, they are meeting in Q4. Now whatever comes, they will always remain together. Okay, similarly, this Q3, Q4, on 1, where are they going? On 1, where are they meeting? You can see Q3 on 1 going to Q5, Q4 on 1 going to Q5. They are both going to Q5. So now whatever comes, they will always remain together. Do you agree? So this is what I'm saying, that this Q3, Q4 on strings that start with 0, they will always remain together. On strings that start with 1, they will always remain together. So remember, whether your string is starting with 0 or starting with 1, this Q3, Q4, they will always remain together. Non-final together, final together. So what I can say, can I say they are equivalent? Q3, Q4. Yes, they are equivalent. Do you agree? So remember, Q3, Q4, you can merge. You can consider them as a single state. What you can do, you can consider them as a single state. Okay, so consider this as a single state, that this is a single state. Okay, this is a single state Q3, 4. Okay, is this point clear? So you can merge and you can consider this as a single state. Now you tell me which other thing you will check. Okay, now you check this Q1 with Q3, Q4. Tell me this is Q1 with Q3, 4. What about this one? Are they distinguishable? Yes, they are distinguishable by whom? They are distinguishable by 1. They are distinguishable by 1. On string 1, you can see Q1 is going to non-final and Q3, 4, they are going to final. Okay, so you can see this Q1 is different from Q3, 4. So I can say Q1 is not mergeable with Q3, 4. What about Q1, Q0? What about Q1, Q0? Tell me. What about this Q1, Q0? You can easily see, okay, just see 0, 1. On string 0, 1, Q1 is going to final and Q0 on 0, 1, it is going to non-final. So they are also not equivalent. So Q1 is not equivalent to Q0 also. Okay, and what about Q0, comma Q3, 4? What about Q0, comma Q3, 4? What about these? So you can see string 1, Q0 is going to non-final and this Q3, 4 is going to final. So very simple that Q0 is also not equivalent to Q3, 4. So finally, in the minimal DFA, how many states will be there? So you can see these I can merge, nothing else. Okay, these two I can merge, and we have already removed this state Q2. There was Q2 that we have already removed. So finally, minimal DFA has how many states? Minimal DFA has 1, 2, 3, 4, 4 states. There are 4 states in the minimal DFA. Okay, very simple. Now let's move on. Okay. Now, to check if two states are equivalent, is it necessary you have to check all the strings? You might be thinking, some of you might be thinking, sir, there are infinite number of strings, strings of length 0, strings of length 1, strings of length 2, 3, 4, 5. Yes or no? There are infinite number of strings. So if I want to check two states are equivalent or not, do I have to check all the strings? Do I have to check all the infinite number of strings? Do I have to check all the strings? Tell me. Do we really have to check all the strings? Let me tell you the answer. The answer is no. You don't have to check all the strings. Let me give you a very nice thing that you only have to check strings of length at most n minus 2. This will save you a lot of time. Now let me tell you, this will save you a lot of time. Basically, you only have to check strings of length at most n minus 2. Strings of length less than equal to n minus 2, where n is the number of states in the DFA. What is n? N is the number of states in the DFA. So remember, we only have to check strings of length at most n minus 2. Is this clear? So remember, if you want to check two states are equivalent or not, you don't have to check all the strings. You can check all the strings with length less than equal to n minus 2. Okay, let's see this example. How many states are there? Tell me. Number of states n. What is that? Tell me. In this DFA, number of states, that is 6. Yes or no? There are 6 states. You can see. Let's call it state number 1, state number 2, state 3, state 1, 2, 3, 4, 5, 6. Okay. So let's assume these are the transitions on A, symbol A. Okay. Now you tell me. So you can easily see number of states, that is 6. So tell me, for any two states, okay, for any two state, if you want to check they are equivalent or not, which strings at most, which strings you have to check? You have to check strings of length at most 4. Yes or no? So remember, we only have to check, we only have to check strings of length at most 4. At most 4. Because what is 4? 4 is n minus 2. At most length 4. That's it. Nothing else. Is this clear? You don't have to check all the strings. You only have to check strings. Okay, we only have to check strings of length at most 4. Is this point clear? Please tell me. Let me know. So remember, let's check. First of all, which states you will check? Will you check? Will you check final, non-final state? Tell me. Will you check a final and non-final state? Will you check? This is your state 1, state 2, state 3, state 4, 5, 6, symbol A. Okay. Now you tell me which states you are going to check. So you are only going to check the non-final states. Also, you are going to check the final states. Okay. So first, let's check the final state. You only have to check 2, 5. Yes or no? So tell me, What about state 2 5? What about state 2 comma 5? Okay, so 2 5, remember, you only have to check strings with the length at most 4. So you have to check only these strings which have length at most 4. That's it. We only have to check these strings, nothing else. Tell me, on empty string, both are going to final. On string A, both are going to non-final. So far, everything is good. On string double A, both are going to non-final. On string triple A, both are going to final. On string 4A, both are going to non-final. So can I say they are equivalent? Tell me. Yes, you can see on every string of length at most n minus 2. On every string of length at most n minus 2, you can see. On every string of length at most 4, you can see both are going to final, non-final together. Yes or no? Here you can see final together, non-final together, non-final together, final together. So I can say they are equivalent. Yes or no? Is this clear? So remember, state 2 is equivalent to state 5. State 2 is equivalent to state 5. Is this clear? So can you notice this method is very good? Do you agree with me that this result is very good, that you only have to check strings of length at most n minus 2. You don't have to check all the strings. You don't have to check all the strings. You only have to check strings of length at most n minus 2. Okay, for any two states, you have to check the strings of length at most n minus 2. That's it. So these strings which have length less than equal to n minus 2, these are sufficient. Okay. So here you can easily see that state 2 5 they are equivalent. Okay. What about state state 1 3? Tell me about state 1 3. Let me know. What about state 1 3? Tell me. State 1 3. Can you tell me? So state 1 3 they are not equivalent. They are clearly not equivalent. Why? You can easily see on the symbol A, on the string A, 1 is going to final, 3 is going to non-final on string A. So they are not equivalent. Yes or no? So 1 is not equivalent to 3. Okay, agree? What about 1 6? What about 1 6? Let me tell you, 1 is not equivalent to 6 also. Okay, the same idea you can apply. They are distinguishable by string A. Okay, next, what about 3 4? What about 3 4? 3 4 are also not equivalent. Okay, then who is equivalent? You check 1 4. Tell me about 1 4. See, 3 4 are not equivalent. Let me tell you, 3 6 are not equal. 3 6 are equivalent actually. We will see. 3 4 not equivalent. 3 1 not equivalent. Okay, 1 6 not equivalent. And 1 4. Yes, they are equivalent. Okay, so let's check 1 4. Let's check state 1 comma 4. For state 1 comma 4, what are you going to check? Tell me. State 1 4. Which strings you are going to check? Strings of length at most 4. Strings of length at most n minus 2. Okay, so just check these strings. Just check these strings. You can see on empty string, both are going to non-final. On string A, both are going to final. On string double A, both are going to non-final. On string triple A, both are going to non-final. On string 4A, both are going to final. Okay, yes or no? So can I say they are equivalent? Yes. You can see state 1 comma 4 on every string of length at most n minus 2. You can see they are always going to final, non-final together. So I can say that 1 is equivalent to 4. Okay, and similarly, remember 3 comma 6 are also equivalent. Okay, is this clear? So remember here, similarly, you can check that 3 is equivalent to 6. Okay, so I can say 3 is equivalent to 6. 1 is equivalent to 4, 2 is equivalent to 5. So finally, in the minimal DFA, how many states are there? In the minimal DFA, how many states? Minimal DFA will have only 3 states. There will be only 3 states, remember? Okay, your initial state will be 1 4. This will be your initial state. On symbol A, you will go to state 2 5, which is final state. On another symbol A, you will go to state 3 6. And on another symbol, you will go to state 1 4. Okay, is this clear? So this is your minimal DFA. Please tell me, is this point clear? So very easy. Let's see this question. What is the step number 1 in the minimization of DFA? Let's minimize this DFA. The step number 1 is remove the unreachable states. Yes or no? So this state you can remove because this is a unreachable state. So I can easily remove it. Yes or no? This state Q5 I can remove because it is unreachable. Okay. So this state Q5 is gone because that was unreachable. So that we have removed. Okay. Is there any other unreachable state? No, every other state is reachable. Okay, now you tell me which states will you check? See, these are final states. You will check these and you will check the non-final states. Okay, so let's check Q3, Q4. Tell me about Q3, Q4. Yes, they are equivalent because on every string, they will always go to final. Can you notice? State Q3, Q4, whatever string you take, any string W you take, they will always go to final. Both are always going to final. So I can say that Q3, Q4, they are equivalent. You can merge them. Okay. So you can consider them as a single state. Remember. Okay. Is this clear? This Q3, Q4, this you can consider as a single state. You can consider them as a single state and you can call it Q3, 4. Okay. Is this clear? Now you tell me, what about state Q1, Q2? What about state Q1, Q2? See, very simple. This state Q1, Q2. If string is starting with 0, see, on empty string, both are going to non-final. Okay, on empty string. If string is starting with 0, where are they going? If string is starting with 1, where are they going? Tell me. This Q1, Q2. Notice this Q1 and Q2. If string is starting with 0, they are going to, they are both going to Q2. Yes or no? Can you notice? Look at this state Q1, Q2. Okay, if string is starting with 0, on 0, they are both going to Q2. Okay, they are both meeting in Q2. So here, from here, whatever comes, they will be together. Yes or no? What about these states on strings starting with 1C? Both will meet in which state? On symbol 1, both will go where? You can see this Q1, Q2. On symbol 1, they are going to single state Q3, 4. Remember, Q3, 4 is single state. So remember, this state Q1 is also going to Q3, 4 and this state Q2 is also going to Q3, 4. So both are meeting in Q3, 4. And from here on anything, they will always be together. They will always be together. Okay, so can I say that this Q1, Q2, look at this Q1, Q2. If string is starting with 0, then also both are together. If string is starting with 1, then also both are together. So can I say they are equivalent? Yes, they are equivalent. Okay, is this clear? So Q1, Q2 are equivalent. So remember what we found. So far, what we found they are equivalent. They are equivalent. We will merge them. Okay, we found they are equivalent. We will merge them. Okay, what about Q0, Q1? Tell me quickly. What about Q0 and this Q1? Are they distinguishable? Yes. By string 1, yes or no? You can notice this Q0 on string 1, it is going to non-final. And this Q1 on string 1, it is going to final. So I can say that Q0 is not equivalent to Q1. Okay, is this clear? So very simple that in the minimal DFA, how many states will be there? Tell me, in the minimal DFA, how many states will be there? There will be only 3 states. There will be only 3 states. Okay, is this point clear to everyone? Please tell me. So we will have only 3 states in the minimal DFA. If you minimize this DFA, you will get only 3 states. Remember, this is unreachable state. So you can remove this unreachable state and these are equivalent and these are equivalent. So minimal DFA will have only 3 states. Okay. And let me tell you that minimal DFA is unique for any regular language. The minimal DFA is unique means there is exactly one DFA with minimum number of states. Okay, is this clear? So remember, suppose D is a DFA with no unreachable state, then when can I say this D is minimal DFA? When can I say this D is minimal DFA? See, D is a DFA with no unreachable state. There is no unreachable state in the DFA D. Now, when can I say this is minimal or I can say minimum? This DFA is minimal or I can say minimum if all the states are distinguishable. If no two states are mergeable. Okay, yes or no? When can I say this DFA is minimal? This DFA is minimal if no two states are mergeable. No two states are equivalent. Means all the states, they are distinguishable from each other. Let's solve this question. Is there any unreachable state here? In this diagram, in this DFA, is there any unreachable state? There is no unreachable state, right? Okay. So now what you will do? Tell me which states you will check. You will check these states because these are final states. You will check them, and you will check these three because they are non-final. So you tell me about Q2, Q4. What about Q2, Q4? Are they equivalent or are they not equivalent? Tell me. Q2, Q4. You can see on string 0, Q2 is going to non-final, Q4 is going to final. So they are definitely not equivalent. Q2, Q4, they are not equivalent. Okay. So you cannot merge them. Is this clear? Okay. What about Q0, Q1? Tell me, what about Q0, Q1? Tell me. You can see on string 1, Q0 is going to non-final, Q1 is going to final. So they are also not equivalent. Okay, Q0 is also not equivalent to Q1. What about Q0, Q3? Tell me, what about Q0, Q3? You can see on string 1, Q0 is going to non-final and Q3 is going to final. So they are also not equivalent. Okay, is this clear? So Q0 is not equivalent to Q3. Very simple. Okay, what is remaining then? What we have to check? Tell me, what is remaining to check? Let me know. So you can see Q1, Q3 are remaining to check. Okay, tell me, what about Q1, Q3? Let's check Q1, Q3. On empty string, both are going to non-final. Okay. If string is starting with 0, if string is starting with 0, where are they going? If string is starting with 1, where are they going? See, notice Q1, Q3. Okay, please focus here. This state Q1, this state Q3. If string is starting with 0, where are they meeting? Q1, Q3. If string is starting with 0, both are meeting in Q2. Yes or no? Both are meeting in the state Q2. Now, from this state Q2, they will always go together. Yes or no? Whatever comes. Do you agree that whatever comes, they will always remain together? Together in final, together in non-final? Okay, very simple. Now, similarly, this Q1, Q3, on 1, where are they meeting? On 1. This Q1, Q3, Q1, Q3, on 1, they are meeting in Q4. They are meeting in Q4. Now, whatever W comes, now whatever comes, they will always remain together. They will always remain together. So this is what I'm saying that, okay, on empty string, Q1, Q3, both are going to non-final. And if string is starting with 0, both are together. If string is starting with 1, both are together. So can I say they are equivalent? Yes or no? Can I say they are equivalent? Yes. This string, this state Q1 is equivalent to Q3. So I can merge them. I can merge them. So in the minimal DFA, how many states will be there? Tell me. So the minimal DFA will have how many states? There will be total 1, 2, 3, 4. 4 states will be there. Okay, there will be total 4 states. Let me create the minimal DFA. It will be like this. There is Q0. On 0, where we will go? See, on 0, 1, we will go to Q13. Okay. And from Q13, on symbol 1, we will go to Q4. And on symbol 0, we will go to Q2. Okay. We will go to Q2. So like this. And you can easily see from Q2 on 1, we will go here. And on 0, we will go here. So this will be your minimal DFA. You can create the minimal DFA. There will be 4 states in the minimal DFA. And when you merge Q1, Q3, this is the minimal DFA you will get. Okay. So very simple. So let me tell you that this is the minimal DFA you will get. This is minimal DFA. Okay. So we have seen the method 1 for minimization of DFA. If a DFA is given to you and you want to minimize this DFA, then we have seen the method number 1, that is we will find the equivalent states and we will merge them. Basically, in this method number 1, we are using the definition of distinguishable states and indistinguishable states, and we are minimizing the DFA. Yes or no? Can you notice in this method number 1, we are using the definition of equivalent state and distinguishable state. Yes or no? So using the definition, we are doing the minimization of a DFA. Okay. And I told you what are the steps. The first step is remove the unreachable state. Don't forget about this step. Okay. So remember step number 1, that is first you remove unreachable state. Then you find what are equivalent states and you merge equivalent states, and then you will get your minimal DFA. Okay. I told you that there is another method for DFA minimization, that is Hopcroft partition algorithm, or I can say Hopcroft algorithm. So this Hopcroft algorithm also we will discuss. We will do a lot of practice of this algorithm also. But let me tell you that this Hopcroft algorithm, this is inefficient, or I can say in the questions we will not use it. So you can see we will rarely use it in the questions. Most of the time we will use this first method, that was use the definition of equivalent states and distinguishable states, and after finding the equivalent states you merge them. So remember your method number 1, that was actually fast and efficient. Okay. So now let's discuss this method number 2. Now the method number 2 for minimization of DFA we are going to discuss, this is Hopcroft algorithm, or you can call it Hopcroft partition algorithm. Okay. So let's discuss this algorithm. Let's discuss. So first, let me tell you the idea of this algorithm. See, this is an algorithm. Let me tell you. This is just an algorithm. Means there will be a sequence of steps. You basically just have to follow the steps. Okay, is this clear? So remember, this is just an algorithm. Means you have to follow the steps, nothing else. Okay, is this clear? So now, what is the idea of this algorithm? Let's discuss. The idea is this. First, you remove the unreachable states. Okay, first you remove every unreachable state, you remove. After that, now what we will do? We will create distinguishable groups of states. Okay, what we will do? We will create distinguishable groups of states, we will create, and iteratively we will find more distinguishable states. Okay, and at the end, the states which are in the same group, they will be equivalent. Okay, at the end of the algorithm, the states which are in the same group, they will be equivalent. So this is the idea. Let me tell you with example, this will become very clear. But this idea on your screen, this you should understand that first you remove the unreachable states. Then what you do? Then you create distinguishable groups of states. Okay, and iteratively we will find more distinguishable states. At the end of the algorithm, the states which are in the same group, they are equivalent. Okay. So let's see the idea of this algorithm. Let me tell you. The starting point will be you remove all the unreachable state. This is your starting point. Okay. After that, what we will do? We will create distinguishable groups of states. So let me tell you the idea is like this. See, just understand the idea. Then with example, this will become very clear. The idea is like this. In this algorithm, what we are going to do? We are going to create some groups, distinguishable groups of states. Okay, like this. For example, maybe this is your group G1, this is group G2, this is your group G3. Okay, so we will create the groups of states. Okay, for example, in this group, there will be states. There will be state P, Q, and something like that. There will be states here also, and there will be states here also. Okay, is this clear? So we will create groups. This is a group, this is a group, this is a group. So groups we will create. Okay, now what we are going to do iteratively from this pi m, I will discuss what is this pi m, don't worry. Okay. From this set of groups, we will find pi m plus 1. The next set of groups we will find means from this set of groups, we will find the next set of groups. Okay. And if you want to go from pi m to pi m plus 1, then let me tell you, only alphabet symbols you will check. Okay, so okay, if you want to go from pi m to pi m plus 1, what you are going to do, only check, okay, what we will do, only check alphabet symbols, means only check a comma b. Okay, is this clear? We will only check alphabet symbols a comma b. Now the idea is like this. The idea is, okay, let's take this p comma q. Within this group we have p comma q. So for this p comma q, what we are going to do, if p comma q on every symbol, if they are going to same group, for example, let's assume on symbol a, let's assume both are going to group 2. Okay, on symbol a they are going to same group, yes or no? Also on symbol b also they are going to same group. Remember, let's assume on symbol a they are going to same group, and on symbol b they are going to same group. So you can notice, on both the symbols they are going to same group, they are going to same group. So I can say that in this pi m plus 1, we will keep them together. We will keep them together. This pq, we will keep them together. Okay, is this clear? So remember, pq together, we will keep them together in a pi m plus 1. Okay, this is the idea. Now let me tell you, if this happens that in this pi m, this pq are together, now we want to find pi m plus 1. So we will only check ab, I told you. Now if this happens, for example, let's assume on a or b, okay, on a or b, remember, on a or b, either a or b, on a or b, on at least one of them, if this happens that this pq, this p is going to, let's assume, some group, and q is going to some other group. Let's assume p is going to some group, for example g2, and q is going to some other group, let's assume g1. Okay, on a or b, remember, I'm saying on a or b, if this happens that they are going to different groups, now what will happen? Now this pq will not be in the same group in the pi m plus 1. Okay, is this clear? We will put them in different groups. Please tell me, did you understand? So remember, if p comma q on a or b, if they are going to different groups, if they are going to different groups, then remember what we will do, this pq we will separate in pi m plus 1, we will separate them. So this is the idea. Now you might be having some confusion, don't worry, with example this algorithm will become very clear. This is a very simple algorithm, let me tell you. Okay, very simple algorithm. When we take examples, then it will become very clear. Let me tell you the initialization of this algorithm. The initialization of this algorithm will happen from pi 0. Okay, the initialization will happen by pi 0. Okay, pi 0 means basically all the non-final states we will put in the same group, and all the final states we will put in the same group. Means here we will put all the non-final states, and here we will put all the final states. This will be your initialization. This is the initialization. From pi 0 we will go to pi 1. From pi 1 we will go to pi 2, and so on. Now if 2 pi are same, for example, let's assume pi 1 pi 2 are same, then we will stop. Okay, is this clear? Please tell me. So like this we are going to go. Remember, like this we are going to go. Okay, I hope you understood that. Like this we will go. And when, so let me tell you here that when pi m is same as pi m plus 1, then we stop. Then we stop. Then we stop this algorithm. Okay, and when you stop this algorithm, then all the states that are together, they are equivalent. Okay, is this clear? All the states which will be in the same group, they will be mergeable. You can merge them. Okay, so the algorithm will stop when pi m equal to pi m plus 1. Okay, so with example this will become very clear. Right now you might be having some confusion, don't worry. Let's take a lot of examples. Let's start with this DFA. Let's minimize this DFA with help of partition algorithm. Okay, so let's see this. Tell me what is the first step. The first step, can anyone tell me what is the first step of the algorithm? Step number 1 of the algorithm, that is remove the unreachable states. First you have to remove unreachable states. Is there any unreachable state? There is no unreachable state. So remember, first step, that is remove all the unreachable states. So there is no unreachable state. Now what you can do, now you can start with pi 0. Okay, what will be pi 0? Pi 0 means all the non-final together, all the final together. Okay, so you can see ABCD will be together, remember? ABCD, these states will be together, and this state E will be separate. Okay, now there is nothing to check here because we only have one state here in this group. In this group, there is only one state. So there is nothing to check here, but these we will have to check. So from pi 0, we will go to pi 1, remember. Okay, and I told you that if you want to go to pi 1, then you only have to check A comma B. You only have to check the alphabet. You only have to check sigma. Yes or no? And what is your sigma? In this question, what is your sigma? Sigma is 0 comma 1. Okay, you only have to check sigma. I told you that when you are going from pi m to pi m plus 1, you only have to check the sigma. Okay, you only have to check sigma. This is what you have to check. So in this diagram, you can easily see that sigma is 0 comma 1. So remember, we will check sigma. Sigma is 0 comma 1. We will only check 0 comma 1. Okay, now what we will do? We will check these states. Okay, like we will check AB, we will check AC, we will check AD, we will check BC, we will check BD, like that. Okay, is this clear? Okay, so let's check AB. Tell me, AB on 0, where are they going? In this diagram, look at this diagram. AB on 0, where are they going? AB on 0. They are going to group G1. Yes or no? Now only group matters. This is a group, this is a group. Only group matters now. Please understand, now only group matters. Let's call it group G1. Let's call it group G2. Only the group will matter now. Okay, is this clear? So tell me, let's check AB. I am checking AB. On 0, where are they going? This AB on 0, they are going to group G1. Okay, so there is no problem. On 0, they are going to group G1. On 1, where are they going? AB. AB on 1. See, A on 1, it is going to group G1, and B on 1, it is going to group G2. So we will separate them. Okay, is this clear? Means A comma B, they will not be together. A and B, they will be separated. In the next A comma B, they will be separated. Is this clear? Tell me. See, very simple point. What I'm saying, you can easily see that your pi 1, your starting point is pi 0. In the pi 0, you have A, B, C, D. Okay, and so this is your pi 0. Correct. Now, in this pi 0, let me tell you that from this pi 0, we will go to pi 1. Okay, and for that, what we will do? We will check only alphabet. What we will check? We will check only alphabet, that is 0 comma 1. Okay, now what we are doing? We are checking this state A comma B. Okay, let's check state A comma B. So now you can easily see that only group matters now. Okay, this whole group, let's call it group G1, and this whole group, let's call it group G2. So the group will matter. Now you can see this A comma B on symbol 0, they are going to same group. Notice on symbol 0, they are going to same group. That is your group G1. Okay, on symbol 0, they are going to same group. So this is fine, but notice on 1, where are they going? On 1, A is going to group G1 and B is going to group G2. So that is the reason I can say that because of this, please focus. Because of this, what will happen? Okay, this A and B will be separated. Okay, is this clear? A and B will be separated in this pi 1. A and B will be separated. So we have separated AB. Okay, now we will check AC. Tell me, what about AC? Let me know. Can anyone tell me about AC? Okay, so let's check AC. On 0, where are they going? A comma C. A comma C. This is a AC. On 0, they are going to G1. Yes or no? See, I am checking AC. On 0, they are going to group 1. Okay, on 1, there, where are they going? On 1, A is going to group 1 and C is going to group 2. Yes or no? A is going to group 1 and C is going to group 2 on 1. So this C will be separated from A. Yes or no? Remember, C will be separated from A. Definitely C will not be here. C will be separated from A. But now there is an interesting question. What about B comma C? Will they be together? See, C will be separated from A. C will be separated from A. But what about BC? Okay, let's quickly check BC. This BC on 0, where are they going? BC on 0, they are going to group 1. Okay, on 1, where are they going? This BC on 1, they are going to group 2. Yes or no? Okay, so BC on 0, they are going to group 1. On 1, they are going to group 2. So they will be together. So BC will be here. Very simple. Okay, what about AD? Tell me, what about AD? Look at AD. AD. Remember, on 0, A is going to group 1 on 0, and D is also going to group 1, means AD. This AD on 0, they are going to group 1. What about on 1? This A on 1, it is going to group 1, but D is going to group 2. Yes or no? So A on 0 going to group 1, and D on 0, it is going to group 1. But on 1, A is going to group 1, but D is going to group 2. So AD will be separated. So definitely AD will be separated. But what about BD? But what about BD? Means, will D be here or D will be separated? We have to check D will be in this group or D will be separated. So let's check BD. Let me check BD. So tell me, BD on 0, where are they going? This BD. BD on 0, they are going to group 1. Yes or no? BD on 0, they are going to group 1. On 1, where are they going? This BD. On 1, they are going to group 2. Yes or no? This BD on 0, they are going to group 1. On 1, they are going to group 2. So they will be together. That's it. Now there is nothing to check. Yes or no? Is this clear? So this is your pi 1. Now you can see pi 0, pi 1 are different. So what we will do? We will go to next pi 2. Now remember, in this group only one state is there, so there is nothing to check. In this group only one state, so there is nothing to check. Now we have to check BCD. Okay, is this clear? So tell me about BCD. Now remember, there are three groups. Now let's call it group G1, let's call it group G2, and let's call it group G3. So tell me, what about BC? BC on 0, where are they going? BC on 0, they are going to group 2. Okay, BC on 0, they are going to group 2. No problem. Okay, what about BC on 1? BC on 1, they are going to group 3. So no problem. So remember, BC will be together, no problem. Okay, is this clear? I can say BC will be together, there is no problem. Okay, what about BD? Let's check what about BD. Tell me, BD on 0, where they will go? BD on 0, they are going to group 2. Yes or no? B comma D on 0, they are going to group 2. And on 1, where are they going? BD on 1, they are going to group 3. So I can say that they also will be together. Okay, yes or no? Is this clear? Please tell me. Let me know. So you can see, remember, BC will be together definitely. And you can see BD also will be together. So finally, that's it. Okay, can I say that you got pi 1, pi 2 same? Yes or no? Can I say pi 1, pi 2 same? So you can see, because pi 1, pi 2 same, so you can stop now. Pi 1 is same as pi 2, so stop. Okay, and finally I can say that there will be three states. Is this clear? These you can merge. BCD you can merge. So I can say that there will be three states in the minimal DFA. Three states in minimal DFA. And these are the three states. Remember, this, and this. Is this point clear? This one, this one, this one. These will be the states in the minimal DFA. Okay. Please tell me, did you understand? Is this point clear? See, this is a very simple point. A student is asking, sir, can you explain pi 2? From pi 1, we are going to pi 2. Okay. Now we have to check these states. We have to check. Remember, in this group, there is only one state. So there is nothing to check. In this group, there is only one state. There is nothing to check. We have to check this group. Okay. Let's check BC. In this pi 1, we are checking. In this pi 1, we are checking BC. BC on 0, where are they going? Tell me. Quickly tell me. BC on 0, where are they going? On 0, they are going to group 2. Yes or no? BC on 0, they are going to group 2. So on 0, there is no problem. Now BC on 1, they are going to group 3. So on 1 also no problem. So remember BC on 0 also same group. BC on 1 also same group. So on 0 comma 1 they are going to same group. So can I say they will be together? Do you agree? In pi 2 they will be together. They will be together here. Okay. Now let's check BD, or you can check CD, whatever. You can check BD or you can check CD. So let me check CD. Okay, no problem. Let me check CD, because you already know that BC are together. You already know BC will be together. Okay, now let's check CD. So you can see CD on 0. Where are they going? CD on 0. They are going to group 2. So CD on 0, they are going to group 2. They are in the same group, no problem. Now CD on 1, where are they going? CD on 1, they are going to group 2, group 3. CD on 1, they are going to group 3. So they are again going to the same group, yes or no? So remember, CD are going to the same group. On 0, they are going to same group. On 1, they are going to same group. So they will be together. Already BC is together. Already BC is together. Now CD also will be together. So ultimately they will be together. Okay, now you can see pi 1, pi 2, they are same. So you can stop. And finally, you will have 3 states. Let me tell you, this will be a single state in the minimal DFA. So remember, this will be one state, this will be another state, and this will be another state. So remember, this will be a single state in the minimal DFA. Okay, is this clear? So let me tell you the minimal DFA you will get. What are the minimal DFA you are getting? For this diagram, the minimal DFA will be having 3 states. Okay, there will be state A. On 0, 1, you will go to state BCD. Okay, on 0, there is a self loop. On 1, you are going to state E. Okay, that's it. Is this clear? Please tell me. This is the minimal DFA you will get. So did you understand the partition algorithm? Let me know. Let me know. Did you like the partition algorithm, or did you like the method number 1, using the definition of equivalent states, distinguishable states, and doing the minimization? So did you like the method number 1 or method number 2? Yes, definitely method number 1. But still, we are learning the method number 2. Did you understand the method number 2? That is my question. You tell me. Did you understand the Hopcroft algorithm? Okay, let's do a lot of practice. Is this DFA minimal? Okay, let's check it. Let's apply the Hopcroft algorithm. In this DFA, let's apply the Hopcroft algorithm. So you have these states P, Q, R, S. These are the states. So let me apply. What is the first step in the algorithm to check whether this is minimal or not? What is the step number 1? Remove the unreachable states. Is there any unreachable state? Is there any state which is unreachable from the initial state? No, every state is reachable. Okay. Now what we will do? Now we will start with pi 0. What is pi 0? All the non-final together, all the final states together. So pi 0 will be PR together, QS together, PR together, QS together. Okay, yes or no? Now from pi 0 we will go to pi 1. Is this clear? From pi 0 we will go to pi 1. Okay, so remember, when you are going from pi 0 to pi 1, what you are going to check? You are only going to check sigma. You are only going to check sigma, that is 0, 1. Okay, so remember, you will only check sigma. Sigma is 0, 1. So this is what you will check. Okay, let's check PR. Let me check PR. Remember, there are 2 groups now. Okay, in pi 0, there are 2 groups. Let me call it group number 1. Let me call it group number 2. Okay, so tell me, PR on 0, where are they going? On 0, where are they going? PR. P on 0, going to group number 2. R on 0, going to group number 2. Both are going to group number 2. So far it is fine, right? Yes or no? PR on 0, going to group number 2. That is fine. That is fine. Okay. So that is fine. I can say. What about PR on 1? What about PR on 1? See, P on 1, going to group 1. R on 1, going to group 1. So can I say they are going to group 1? So remember, on 0 also they are going to same group. On 1 also they are going to same group. So this is also fine. So can I say they will stay together? In pi 1, they will remain together, PR. Do you agree that they will remain together, PR? Okay, because on 0 also they are going to same group, on 1 also they are going to same group. So PR will be together. Okay, so remember here in this pi 1, definitely PR is together, no problem. Okay, now let's check QS. What about QS? Tell me. Where Q will go on 0? Remember, we have two groups. There is group number 1, there is group number 2. We have two groups. Okay, so tell me, this QS, where they will go on 0? You can see they are going to group number 2. Both are going to group number 2. So this is also fine. You can easily see QS on 0, they are going to group number 2. This is your group number 2. So QS on 0, they are going to group number 2. Okay. What about QS on 1? What about QS on 1? QS on 1. See, this is your group number 1. QS on 1, they are going to group number 1. Do you agree? They are going to group number 1. So this is also fine. So can you notice QS on 0, they are going to same group. On 1, they are going to same group. So can I say again, they also will be together. Okay. So can I say pi 0, pi 1 are same? Pi 0, pi 1, they are same. So stop. So stop. Yes or no? So yes, this is a now in this situation, now you can stop. So I can say this will be your single state. Yes or no? So there will be two states. Can I say there will be two states? So remember, minimal DFA will have how many states? Tell me. Minimal DFA will have how many states? Minimal DFA will have two states. One state will be PR. This will be your initial state. And another state will be QS. Okay. So there will be two states. Is this point clear? So this will be one state. Another state will be this. This is your minimal DFA. Please tell me, did you understand? Let me know. Okay. So remember, this is not a minimal DFA. The minimal DFA will have two states. We have already found that the minimal DFA will have two states because already P, this is Q, this is R, this is S. So remember, PR will be together. On 1, there will be self loop. On 0, we will go to QS. On 0, there will be self loop. This is the final state. On 1, we are going here. So this is the minimal DFA. Is this point clear? Please tell me. Let's solve this question. We have to find the minimal DFA. A DFA is given to you. Consider the DFA with initial state Q0. Okay, and the final state is Q2. The final state is only Q2. Okay, and total how many states are there? Q0, Q1, Q2, Q3, Q4. Okay, so remember, sorry, Q0 to Q3. That is total 4 states. We have to find the minimal DFA. Okay, so let's apply the Hopcroft algorithm. First, you tell me, is there any unreachable state here? First, you remove, is there any unreachable state? From the initial state, is there any unreachable state? See, initial state is Q0. On A, you can go to Q2. So Q2 is not unreachable. Q2 is reachable. Okay, on A also you are going to Q2. On B also you are going to Q2. So Q2 is reachable. Okay, next you can see from Q2 you can go to Q3. From Q2 on A, on B, you can go to Q3. So Q3 is reachable. Q3 is also reachable. From Q3 on B, you can go to Q1. So Q1 is also reachable. Can I say that every state is reachable? Do you agree with me? That every state is reachable. Okay, so very easily you can see Q1 on A going to Q2. Okay, so very simple. This is the idea. Okay, so you can see there is no unreachable state. Okay, there is no unreachable state. Now let's see, because there is no unreachable state. So now what we will do? Now we will minimize this. Let's apply the partition algorithm, Hopcroft algorithm. We will start with pi 0. What is pi 0? Non-final state together, final state together, non-final state. What are those? Remember, there is only one final state, that is Q2. This is the only final state Q2. So non-final state together, that is like Q0, Q1, Q3. and this is Q2. Now remember, there is only one state here in this group, so there is nothing to check in this group. Now we will find what is pi 1. Okay, so let's check pi 1. Let's check. Okay, what is the alphabet? The alphabet is A comma B. Okay, so remember what we will do? We will check only alphabet. We will check only alphabet, that is sigma. Okay, so you tell me, what about Q1, Q2? Sorry, Q0, Q1. On A, where are they going? On A, where are they going? Tell me. Are they going to same group on A? Because remember, you can call this group 1 and you can call this group 2. Okay, so you can call them group 1, group 2. So now tell me, on 1, where are they going? On A, Q0, Q1. Q0, Q1 on A, they are going to group 2. Yes or no? They are going to group 2. They are going to group 2 on A. Okay. And similarly, remember Q0, Q1 on B also they are going to group 2. Okay. So remember, this is fine. And similarly, this Q0 is Q0, Q1 on B also they are going to group 2. Okay. So remember, this is also fine. This is also fine. So that is the reason I can say they will remain together. Do you agree? Q0, Q1 will remain together. Will remain together. Okay. Now we have to check where the Q3 will go. Yes or no? So remember, already we have found that Q0, Q1 will be together, no problem. Q2 is already separate, no problem. Now we have to check what about Q0, Q3? What about Q0, Q3? Tell me. Q0, Q3. Already remember, this was your group G1, this was your group G2. So tell me, this Q0, Q3 on A, Q0, Q3 on A, they are going to different groups. Can you notice? Can you notice they are going to different groups? Yes or no? They are going to different groups. Notice that Q0 on A, it is going to group 1. Q0 on A, sorry, it is going to group 2. It is going to group 2. And Q3 on A, Q3 on A, it is going to group 1. Yes or no? So we are going to different groups on A. That is the reason I can say Q0, Q3 will definitely be separate. Okay, so this is your pi 1. That Q0, Q3 will be separated. Q0, Q1 will be together. Okay, so remember, we got our pi 1. This is your pi 1. Now pi 1, pi 0 are not same, so we will go to pi 2. Okay, now remember in the pi 2, please notice, now this is your group G1. This is your group G2 and this is your group G3. So there is only one state in this group, nothing to check. There is only one state in this group, there is nothing to check. We have to check only Q0, Q1. Okay, so let me check Q0, Q1. Where are they going on A? Tell me Q0, Q1. Q0, Q1 on A. Q0, Q1 on A. They are going to Q2. Q0, Q1 on A. They are going to group G3. Okay, correct. And what about on B? On B also they are going to group G3. On B also they are going to group G3. Okay. A student is asking, did we have already checked Q0, Q1? No. See, from pi 0 to pi 1, we have checked Q0, Q1. Now we are checking for pi 1 to pi 2. Okay, now the groups are changed. Yes or no? Now the groups have changed. Please notice, for pi 0 to pi 1, we have already checked Q1, Q0. But now the groups are changed. So now we have to check this again. So we are checking this Q0, Q1. Now you can notice this Q0, Q1 on A, comma B. They are going to Q2, which is group G2, which is group G3. So I can say that it is fine. So finally, I can say that they will be together. Yes or no? Q0, Q1 will be together. Q3 will be separate and Q2 will be separate. So that's it. This is your answer. This is the answer. You can see pi 1, pi 2 are same. Pi 1, pi 2 are same. So stop. Okay, so Stop now. So this is the idea. Is this clear? Please tell me. So this is your partition algorithm. Finally, I can say three states will be there in the minimal DFA. Is this clear? So remember, in the minimal DFA, there will be three states. What are those three states? The three states are Q0, Q1, they will be equivalent, they will be mergeable, and Q2, Q3. So remember, three states will be like this: Q0, 1, Q2, and Q3. These will be your three states in the minimal DFA. That's it. Is this point clear? Please tell me, did you understand? So we have found the minimal DFA. Now, let me tell you one thing, that in this Hopcroft partition algorithm, what this pi k means. You might be thinking, sir, what this pi k means? Okay, so let me tell you. See, what is pi 0? Can you tell me? What is pi 0? Pi 0 is all the final states together, all the non-final states together. Yes or no? What was pi 0? That was all the non-final together, all the final together. So can you notice? Can you notice that pi 0 means that this group and this group, they are distinguishable by empty string? Yes or no? Pi 0 indicates what? Indicates distinguishability by empty string. Can I say? Please tell me. Distinguishability by empty string. Can I say? Can I say? Let me know. Pi 0 indicates distinguishability by empty string. Okay, is this clear? Similarly, remember, this pi 1 will indicate, or I can say any pi k will indicate this pi k. What it will indicate? It will indicates distinguishability by whom? Distinguishability by strings of length at most k. Strings of length at most k. Is this clear? So remember, pi 0 indicates distinguishability by empty string. Pi k indicates distinguishability by strings of length at most k. Okay. So this is what I'm saying, that pi k indicates that with respect to strings of length at most k, okay, which are distinguishable and which are equivalent. It is like this. See, let me tell you that in pi k, let's assume that if two states are in the same group, in pi k, let's assume in the pi k, p, q are in the same group, and let's assume r is here, and let's assume s is here. Okay, then remember what this means. Let me tell you what this means. This means that p, q are not distinguishable by any string of length at most k. Okay, so remember, pi k indicates that distinguishability by strings of length at most k. Yes or no? Do you agree? Do you agree? This indicates distinguishability. This indicates distinguishability by strings of length at most k. By strings of length at most k. At most k. Okay, clear? So now you can easily see that if pi k is this, then I can say that here, I can say that for pq, what I can say? Tell me, for pq what I can say? For pq, I can say that they are not distinguishable by any string of length at most k. Is this clear? They are not distinguishable by, they are not distinguishable by any string of length at most k. Okay, is this clear? But for pr, what I can say? For pr, what I can say? Tell me. For pr, what I can say? Let me know. For pr, I can say that they are distinguishable by some string of length at most k. Yes or no? Yes or no? They are distinguishable by, they are distinguishable by some string of length at most k. Okay, is this point clear? Please tell me what this pi k indicates. Did you understand? Pi k indicates that with respect to strings of length at most k, which states are equivalent and which states are distinguishable. For example, pi 0 indicates distinguishability by empty string, means these states are distinguishable from these states by empty string. Okay, now pi k indicates distinguishability by strings of length at most k. Okay, so this is what I'm saying. Now you can easily see that pi k indicates distinguishability by strings of length at most k. So remember, if this is your pi k, then p comma q, they are not distinguishable by any string of length at most k. Remember, remember p comma q, they can be distinguishable by some more length string. Yes or no? P comma q, they are not distinguishable by any string of length at most k, but maybe they are distinguishable by some more length string, by some string of length more than k. Okay, but I can say that till now I can say pi k, if this is your pi k, then I can say that p comma q are not distinguishable by any string of length at most k. And remember, p comma r, they are distinguishable by some string of length at most k. So this is what your pi k indicates. I hope you understood. Okay, let's solve this question. Minimize the following DFA using both the methods that we have studied. For minimization of DFA, we have seen two methods. Okay, method number one, that is very simple method. You use the definition of equivalent states and distinguishable states, and then you find equivalent states and then you merge the equivalent states. Yes or no? That was your method number one. Method number two, that is your Hopcroft partition algorithm. So we have to apply on this DFA, we have to apply both the methods and we have to minimize this DFA. Okay, is this clear? So let's quickly do the method number one. Tell me your favorite method number one, that is your favorite method. Tell me which states you will check in the method number one. You can see these are final states, so you will check 1 4. Also you will check 2 3 5. Yes or no? So let's check 1 4. What you will do in this method number one, you will check state 1 4. Also you will check what? You will check state 2 3 4, 2 3 5. Okay, so let's check 1 4. Are they distinguishable or not? Are they distinguishable or not? State 1 4, they are final states. So tell me, you can easily see by string A, they are distinguishable. 1 on A going to final state, 4 on A going to non-final state. So can I say that 1 is not equivalent to 4? So we cannot merge 1 comma 4. Yes or no? So 1 comma 4, they are not equivalent. You tell me about 2 comma 3 comma 5. You tell me about 3 comma 5. Let me know. What about 3 comma 5? Tell me. On empty string, both are going to non-final. Okay. If string is starting with A, then where are you going? Tell me, if string is starting with A, where are you going? I'm asking 3 5. State 3, state 5. If string is starting with A, then both are meeting where? Both are meeting where? 3 comma 5. Okay, on A, on A, on A, both are meeting in state 1. Okay, so you can see whatever comes now, they will always be together. Do you agree? Okay, so remember, if string is starting with A, they are together. And if string is starting with B, what about then? If string is starting with B, means 3 5. So 3 5 on B, they are going to 2. 3 5 on B, they are meeting in the state 2. They are meeting in the state 2. And now whatever comes, they will remain together. So, so that is the reason I can say if string is starting with B, then also they are together. Can you notice they are equivalent? 3 is equivalent to 5. Correct? Okay, 3 is equivalent to 5. What about 3 comma 2? What about 3 comma 2? Let me know. What about 3 comma 2? Tell me. 3 comma 2. Is there any string which can distinguish them? Yes, you can take double A. You can take double A. State 2 on double A will go to non-final. State 3 State 3 on double A will go to final. So they are not equivalent, yes or no? 2 is not equivalent to 3. So remember, 2 is not equivalent to 3. 3 is equivalent to 5. Okay. And similarly, you can see 2 comma 5 are not equivalent. Why they are not equivalent? 2 comma 5. Why they are not equivalent? Tell me. 2 is not equivalent to 5. What is the reason? 2 is not equivalent to 5. What is the reason? They are distinguishable by whom? They are distinguishable by, again, double A. You can take double A. Yes or no? They are also distinguishable by double A. Okay, 2 comma 5. They are also distinguishable by double A. Very simple. So that's it. So finally, tell me which states are mergeable. I can say state 3 comma 5 are mergeable. Yes or no? State 3 comma 5, they are mergeable states. Okay, we got our mergeable state. These we can merge. So in the minimal DFA, how many states will be there? In the minimal DFA, total how many states? 1, 2, 3, 4. 4 states will be there. Okay, 4 states will be there. So you can easily create the minimal DFA. The minimal DFA will be like this. Notice. Okay, state 1, there is a self loop on A. There is on B, where you will go. On B, you will go to state 3, 5. Okay. And from state 3, 5 on A, you will go to here. And on B, from this state 3, 5 on B, where we will go? On B, we will go to state 2. Okay, from state 2 on B, we will go here. And on A, we will go to state 4. Okay, and from state 4 on B, we will go to here from state 4. And on A also, we will go here. Okay, on A comma B, we will go to 3, 5. So this is your minimal DFA. I hope you understood. There will be 4 states in the minimal DFA. So this method is very nice. Yes or no? This method, using the definition of distinguishable state, equivalent states, this method is very nice. Now, can you apply the Hopcroft algorithm? Let's apply the Hopcroft algorithm. Method number 2. Let's apply method 2. That is your Hopcroft algorithm, partition. Okay, so let's do this. Is there any unreachable state? There is no unreachable state. So let's start with pi 0. Pi 0 means all the final together, all the non-final together. Okay, the final, these are 1, 4, these are together, and 2, 3, 5, these are together. Okay, from pi 0, we will go to pi 1. Now tell me quickly, 1, 4, on symbol A, where are they going? Your sigma, that is A comma B. You just have to check the sigma. Okay, so tell me on A, where are they going? This 1, 4. Let's call it group number 1. Let's call it group number 2. So 1, 4 on A, where are they going? 1, 4 on A, they are going to different groups. Yes or no? See, 1 on A going to group 1, 4 on A going to group 2. They are going to different groups. So can I say they will separated? They will be separated. Do you agree? They will be separated in pi 1. In pi 1, they will be separated. Okay, that's it. Now you check 2, 3. Check 2, 3. 2, 3. On A, where are they going? 2, 3. See, 2 on A going to group 1. 3 on A going to group 1. Yes. Okay. 2, 3 on A, they are going to group 1. So that is fine. Okay. 2, comma 3 on B. 2 on B going to group 2. 3 on B going to group 2. So again, can I say they will stay together? Yes or no? Here they will stay together. Okay, they will 3, 2, 3 will be stay together. What about 2, 5? What about 2, 5? On B, they are going to group 2. I'm checking 2, 5. I'm checking 2, 5. On B, they are going to group 2. On A, they are going to group 1. So yes, they will remain together. Okay, so this is your pi 1. We got the pi 1. Okay, is this clear? This is your pi 1. Now from pi 1, we will go to pi 2. From pi 1, we will go to pi 2. So there is only one state in this group, nothing to check. There is only one state in this group, nothing to check. Now we have to check 2, 3. But remember now this is your group G1. Okay, this is your group G2. And this is your group G3. Okay, now you tell me. Now you check 2, 3. Tell me where 2, 3 will go on A. 2, 3 on A. 3 on A going to group 1. 3 on A. Notice 3 on A going to group 1. 2 on A going to group 2. So they will be separated, yes or no? 2 on A going to group 2. 3 on A going to group 1. They will be separated. So 2, 3 will be separated. Please understand. 2, 3 will be separated. Now let's check with whom 5 will go. See, 2, 3 are separated. Now let's check with whom 5 will go. Let's check 2, 5. Let me check 2, 5. 2, 5. See, 2 on A going to group 2. 5 on A going to group 1. So 2, 5 will be separated. Do you agree? 2, 5 will be separated. Okay, 2, 5 will be separated. Means 5 will not come here. But can 5 come with 3? See, 5 will not come here. But can can 5 be here or 5 will be separated? So let's check 5. Okay, so tell me what about 5? You can see, let's check 3, 5. Let's check 3, 5, 3, 5. On A, they are going to group 1 on A. Remember 3, 5. I'm checking 3, 5. On A, they are going to group 1. And on B, they are going to group 3. Yes or no? They are going to group 3. So I can say that 3, 5 will stay together. Okay, so this is your pi 2. Now let's see pi 3. Now there is only one state in this group, nothing to check. There is only one state in this group, nothing to check. There is only one state in this group, nothing to check. We only have to check 3, 5. Yes or no? Is this clear? We only have to check 3, 5. Now remember, this is your group 1. You can say this is group 2, this is group 3, this is group 4. So now we have to check only 3, 5. You tell me about 3, 5. 3, 5 on A, where they will go? I am checking 3, 5. 3, 5 on A, they are going to group 1. Okay. 3, 5 on B. 3, 5 on B, they are going to group 3. Yes or no? So they will be together. Yes, very good. So they will be together. Now you can see pi 2, pi 3 are same. Now you can see that pi 2, pi 3 are same. So stop. So stop. And finally, how many states will be there? There will be total 4 states in the minimal DFA. In the minimal DFA, there will be 4 states. Please tell me, did you understand? Let me know. So now you tell me which method did you like? This same question we have done using 2 methods, method number 1, method number 2. Which method did you like? Which method will you use? Method number 1. Okay, you can always use the method number 1. Okay, so very simple. And in the method number 1, do you have to check all the strings? See, you can apply the method number 1. Okay, whatever question comes in the gate exam, you can apply the method number 1. In the method number 1, you tell me, do you have to check all the strings? If you are checking 2 states, are they equivalent or not? Then will you have to check all the strings? You don't have to check all the strings. You only have to check the strings of length at most n minus 2. Yes or no? If you are checking 2 states, are they equivalent or not? Are they distinguishable or not? Then you don't have to check all the strings. You only have to check strings of length at most n minus 2. Just check the strings of length at most n minus 2. Okay, where n is the number of states in the DFA, in the given DFA. So method number 1, that is very good. That is brilliant method. That is beautiful method. Honestly speaking, okay, I'm honestly speaking that this method number 2, this Hopcroft partition algorithm, I have never used in any gate question. Also, let me tell you that you also can, if you do not apply this Hopcroft algorithm on any gate question, then also this method number 1 you can apply on every question. Okay, so there is not a single question in the gate exam on which this method number 2 you have to apply. You can always apply the method number 1. This Hopcroft partition algorithm you never have to apply. This is time consuming, boring method. Yes or no? Time consuming and boring method. But the method number 1, that is very interesting method. You can find what are the equivalent states, what are distinguishable states, and to check whether 2 states are equivalent or not, you only have to check the strings with length at most n minus 2, where n is the number of states in the given DFA. So method number one, that is the beautiful method. And I think Go classes is the only institute where method number one is taught. I think because others, they are only teaching the partition algorithm, this boring partition algorithm they are teaching, and this is very boring method and this is very time consuming method. You can always apply the method number one, that is using the definition of equivalent states and distinguishable states. Okay. Can I give this question as a homework? Minimize the following DFA using the methods that we have studied so far. So far, we have seen two methods for minimization of DFA. One is using the definition of distinguishable states and using the definition of equivalent states. Also, the method number two, that is your partition algorithm. So, can I give you this question as a homework? Apply both the methods and try to get the minimal DFA. Okay. So, take this question as a homework. Okay, must apply both the methods. Remember, don't be lazy. Apply both the methods and you minimize this DFA. Okay, try to see that both the methods are giving you the same result. So that's it. Let's solve this GATE 2024 question. Consider the 5-state DFA. This 5-state DFA is given to us. This DFA M accepting the language which is subset of sigma star. So this is accepting some language LM. For any string W, N0, N0W means number of 0 in W, and N1W, that means number of ones in W. Which of the following statements is or are false? So these are the three statements where the question is asking which states are distinguishable and which states are equivalent. This is a GATE 2024 question in which they are asking which states are distinguishable, which states are equivalent. Okay. So this is what we have already seen in this lecture. I hope this has become a piece of cake for you. Yes or no? So let's see. The question is asking state 2, 4. Are they distinguishable? Tell me. Let's check state 2, 4. You tell me about state 2, 4. So state 2, 4, let's check. Okay, are they distinguishable or are they indistinguishable? Are they equivalent or are they not equivalent? So you can easily see that this state 2 and this state 4 on 0, where are they going? On string 0, where are they going? See, state 2 on 0 going to non-final state. Okay, state 4 on 0 going to final state. So can I say that state 2 is not equivalent to 4? So they are definitely distinguishable. Yes or no? 2, 4, they are distinguishable. They are distinguishable states. These states are distinguishable states. Okay. So very easy. So remember, in this question, they are asking false statement. But statement A is actually true statement. Yes or no? This statement A is actually true statement, but the question is asking about false statement. Okay. Now let's check about the next. Let's check what the next, that is state 3, 4. Let me check state 3, 4. Okay. Let me check state 3, 4. Okay. So for state 3, 4, you tell me what will happen. 3 state 3, 4. Okay. On empty string, where are they going? 3, 4. Both are going to non-final state. So far it is good. Okay. Now you tell me state 3, 4. This is what I'm checking. If string is starting with 0, then what is happening? Can you notice that this is your state 3, this is your state 4. Okay. If string is starting with 0, where are they meeting? If string is starting with 0, this is what I'm asking. So you notice state 3, state 4. Okay. If symbol 0 comes in the state 3, state 4, if symbol 0 comes, then they are meeting in the state 1. Yes or no? They are meeting in the state 1. Can I say now whatever comes, now whatever W comes, they will always remain together? Can I say? Can I say now they will always remain together, whatever comes? So I can say that if string is starting with 0, there is no problem, they will always remain together, whether final or non-final, they will always remain together. Do you agree? If string is starting with 0, then final or non-final, they will always remain together. They will always go to final state together, non-final state together. This is your state 3, 4. Okay, but what about string 1? What about string 1? Tell me. 3 comma 4 on string 1. See, 3 on string 1 going to non-final and 4 on string 1 going to non-final. Okay, is this clear? Now you might be thinking, sir, do I have to check all the strings? First of all, you tell me, starting with 1, is there any possibility they are meeting somewhere? See, starting with 1, notice 3 on 1 going to 2, 4 on 1 going to 5. So they are not meeting in the same state, yes or no? Do you agree? This state 3, this state 4, on string 1, they are not meeting in the same state. On 0, they are meeting in the state 1. So after that, they will always remain together. But on string 1, 3 is going to 2 and 4 is going to 5. Okay, so they are not meeting together. So you can easily see on 1, both are going to non-final, non-final. Okay. Now tell me, like this, will you check all the strings which are starting with 1? You don't have to check strings starting with 0 because we have already seen that if string is starting with 0, then state 3 comma 4 they will always go together. Okay, now you tell me, will you have to check all the strings which are starting with 1? Will you have to check all the strings that are starting with 1? The answer is no. I told you that checking strings of length at most n minus 2 is sufficient. Yes or no? We only have to check strings of length at most n minus 2. Here, what is n? Here, n is equal to 5. Number of states equal to 5. So, we only have to check strings of length at most 3. Yes or no? We only have to check. Okay, only need to check strings of length at most 3. Strings of length less than equal to 3. Yes or no? And there also, you don't have to check when string is starting with 0. You don't have to check. Yes or no? You don't have to check when string is starting with 0. Okay, so you tell me, what about 1 0? What about 1 0 and what about 1 1? Tell me quickly. On 1 0, where 3 is going? This is state 3. On 1 0, it is going to non final. And this is state 4. On 1 0, it is going to non final. On 1 1, both are going to final. Yes or no? On 1 1, both are going to final. Now we have to check 3 length strings also. Remember, we have to check 3 length strings also. So 3 4, 3 length strings also we have to check. We don't have to check strings starting with 0. Strings that are starting with 0, that is already done here. Okay, so now we have to check 3 length strings. In the 3 length strings, we have to check these. That's it. These we have to check. So tell me quickly. On 1 0 0, where these states are going? On 1 0 0, both are going to final. You can see 1 0 0, both are going to final. On 1 0 1, 1 0 1, this is going to non final. 1 0 1, this is going to non final. On 1 1 0, 1 1 0, this is going to non final. 1 1 0, this is going to non final. Okay, is this clear? On 1 1 1, 1 1 1, this is going to non final. 1 1 1, this is also going to non final. Okay, is this clear? So that's it. Now you can stop. You only have to check the strings of length at most 3. Now that's it. So can I say that 3 comma 4 are equivalent? Because they are always going to final together, non-final together. They are always going to final together, non-final together. So can I say they are equivalent? Is this clear? So they are equivalent. Finally, the result is that they are equivalent. So I can say that state 3 is equivalent to state 4. Okay, is this point clear? So they are, remember, they are equivalent. 3 comma 4, actually they are equivalent. So this statement is actually false because this is saying that state 3 comma 4 are distinguishable, but they are actually equivalent. So this statement is false. Okay. Now remember, they are equivalent. 3 comma 4, they are equivalent. So you can merge them. Okay, so you can merge them. Correct. You can consider them as same state. Do you agree? Consider 3 comma 4 as a single state. Consider them as a single state. Consider 3 4 as a single state. Okay, now let's check. What the next option? The next option is checking 2 5. Okay, now tell me 2 5. Now I want to check 2 5. Remember, on empty string both are going to non-final. If string is starting with 0, are they meeting somewhere? 2 5. Tell me, this is state 2, this is state 5. If string is starting with 0, are they meeting somewhere? 2 5. If string is starting with 0, yes, they are meeting in 3 4. 3 4 is a single state, remember? 3 4 is a single state. So now whatever comes, they will always remain together. Okay, similarly, if string is starting with 1, are they meeting somewhere? If string is starting with 1, 2, 5. Okay, if string is starting with 1, are they meeting somewhere? Okay, let's look at this. 2 5. If string is starting with 1, they are meeting in state 1. Okay, so from there whatever comes, they will always remain together. So can I say that whether string is starting with 0, they are together? If string is starting with 1, they are together. So can I say they are equivalent? Please tell me. They are always together. Final, non-final, they will always go to final together. They will always go to non-final together. So they are equivalent. Yes or no? 2 5, they are equivalent. Please tell me, did you understand? So remember, state 2 5, they are they are distinguishable. That is false because they are equivalent actually. Okay, is this clear? So remember, 2 5 is equivalent, 2 is equivalent to 5, and 3 is equivalent to 4. Okay, very simple. Now you tell me, what about the remaining? For example, what about 1 2? What about 1 2? Let me know. What about state 1 2? Can anyone tell me about state 1 2? They are not equivalent. State 1 2. Yes, 1 is final. So by empty string, they will be distinguishable. Okay, so there is nothing to check with 1 2. Okay, what about, you can see 2 5 are equivalent, 3 4 are equivalent. You tell me about 3 5. You tell me about 3 5. Let me know. 3 5, are they equivalent? 3 5. They are distinguishable by whom? 3 comma 5. They are distinguishable by whom? That they are distinguishable by 1. 3 on string 1 will go to non final. 5 on string 1 will go to final. So I can say that 3 comma 5, they are actually not equivalent. So in the minimal DFA, how many states will be there? So remember, we got this. These are equivalent, these are equivalent. In the minimal DFA, how many states will be there? In the minimal DFA, there will be 3 states. Okay, there will be 3 states. The state number 1, the state number 2 5, and the state number 3 4. These will be the states in the minimal DFA. Please tell me, did you understand this? Is this question clear to everyone? Let me know. Is there any doubt? Let me tell you, this question you can solve by another method. What is that? See what you can do. The question is asking which states are distinguishable. Okay, so what you can do, just minimize this. Okay, just minimize this DFA. See what you do, you minimize this DFA. When you minimize this DFA, what will happen? State 1 will be there, state 2 5 will merge, and state 3 4 will merge. Now you can easily see they are equivalent. Okay, now you can easily see that 2 4 are distinguishable. This statement is true, and these two statements, these are false. Okay, the question is asking what is false statement. So remember, definitely B is false and C is false. Okay, is this clear? Definitely B will be answer, C will be answer. Okay, so very simple. I hope you understood. Tell me, is this question clear to everyone? The question is asking which states are distinguishable, which states are equivalent. We have already seen this in our lecture, in today's lecture. In this lecture, you have become expert of which states are equivalent, which states are not equivalent. Whatever question they give you in the gate exam, can you solve it easily? And remember one thing. What is that? Tell me. Remember one thing, that to check if two states are equivalent or not, you don't have to check all the strings. You only have to check strings of length at most n minus 2. Here, the number of states n equal to 5. So you have to check only the strings whose length is at most 3. Okay, so very easily you can see, and this question is very easy. So finally, these two BC, these will be the false statement. Okay. Okay, thank you everyone. I hope you loved this session. In this session, we have discussed how to minimize a DFA. A DFA will be given to you. The question will ask you minimize this DFA. Find the number of states in the minimal DFA. You can very easily do it. There are two methods. One method is use the definition of equivalent states, distinguishable states, and using that definition, you minimize the DFA. Find the equivalent states and you merge the equivalent states. Okay. The second method is Hopcroft algorithm, or I can say Hopcroft partition algorithm. That is a boring method, but we have done a lot of practice. In the GATE exam, there is not a single question in which you have to apply the Hopcroft partition algorithm. You don't have to apply this because this is boring, time consuming, and not efficient method, very slow method. This partition algorithm, this is very slow. So remember, in the GATE exam, on any question, you never have to apply the Hopcroft algorithm. You can always apply our method number one, that is just find the equivalent states and you merge the equivalent states. Remember one thing, very important note: before you apply any algorithm, first you remove the unreachable states. Okay, first you remove the unreachable states, then you find which states are equivalent and you merge the equivalent states. Okay, so this is your minimization of DFA. You can see there is a question in the GATE 2024 based on which states are distinguishable, which states are not distinguishable. So this question came in 2024. Okay, so thank you everyone. I hope you loved the session. Now in the next session, we are going to solve each and every GATE PYQ based on minimal DFA. Thank you everyone.